Welcome everybody at the University of Tuscia. Unfortunately, we have to do this again online and not in presence physically. This is the second edition online, by the way. We hope to bring the next edition in presence wherever it will be. But in any case, it is important to continue this conference. I've been part of this community roughly in the last 20 years, and I will leave the floor to my dear friend Sauro Succi to tell you about the DSFD, because he starts his activity in discrete methods few years before me, and he will certainly make a better job to explain the main issues of this conference, which was inaugurated in Los Alamos in 1989. This is my third organization of DSFD. Since in 2010, we organized the Rome edition, which took place in the National Research Council. And it is important, I told you, not to stop this event. It deals with the growing sector of computational physics and computational science, and it covers almost all branches of fluid dynamics, especially those new branches in chemistry, material science, obviously engineering, but also biology, medicine, and so on. And I think discrete methods gave a great contribution to computational fluid dynamics in general. And it's a nice thing to host all these young researchers from all over the world. And let me just thank all the people that allowed such an organization with all the difficulties connected to the COVID-19 pandemic. So I would like to thank the local organizing committee, and in particular Giacomo Falcucci, Claudia Colantonio, who did most of the work, and Stefano Mastro Stefano, who was preparing everything good for the connection and for the website. He managed all these things with all the other things he has to do here. And I would like to thank all the DSFD committee for their support in the organization and in the scientific program. Probably I forgot someone. I have to extend further thanks to our invited speaker, Benedict Dorscher, Tim Kruger, Matteo Lulli, Adriano Tiribocchi, Emanuele Zaccarelli, and obviously Giorgio Parisi. He doesn't need any introduction, as all of you know him as probably one of the most important scientists, and not only in statistical physics. He got plenty of prizes, the Boltzmann Medal, the Dirac Medal, the Max Planck Medal, and recently also the Wolf Prize. And it is an honor for me to have him here, although online and not in presence. I invite him to come to Viterbo as soon as possible to visit our university and to tell something also to our students. Thank you very much, Giorgio, for being here. And finally, I would like to thank Sauro, who introduced me in this topic many years ago, more than 20 years ago.
A few years ago, Stefano.
A few years ago. And thank you very much, and have a good conference. Thank you.
Okay. Thank you, Stefano. So it is my turn, Giacomo, I guess.
Yes, please.
Okay, so thank you, Stefano. I'm sorry, I was prepared to introduce Giorgio myself, so you stole my show, but that's okay. Just a few words.
You have plenty of things to say about Giorgio. I just put a few things.
So first of all, thanks to Stefano, because he keeps actually offering us the possibility to keep going with DSFD, notwithstanding the hardship of the COVID. So thanks a lot, Stefan, and thanks actually to all your collaborators you just mentioned. Last year, I had an explicit talk on the history of the DSFD. I don't think I'm going to give this talk again. I just remind the youngest people in the audience that indeed it started when even me, I was young at that time. That tells you all. In 1986, and ever since, as Stefano was pointing out, each time I look at the breadth of the application of discrete methods, particularly Lattice-Boltzmann, but not only Lattice-Boltzmann, I'm amazed at the breadth of application, not only in fluids, more and more in soft matter, with some aspect of biology, engineering. And so I think we should be all proud as a community of this success. And one of the hallmarks of our conference that we always wanted to have high key speakers speaking about related subjects, but not necessarily strictly on the DSFD subjects. And this year, we are really extremely honored to have Giorgio with us. Giorgio is a very dear friend, I must tell you, is a magnificent human being before we talk science, because everybody knows Giorgio is the pride of any Italian scientist. I will not mention all of these prizes because this will exhaust the conference. But one thing I want to say, and that's very private, that Giorgio is really a very, very nice person. Despite all this business, he has been the president of the Accademia Lincei. He's always available, he's always in good temper. He's really, I'm really very grateful, and I really wanted to say that in public. So thank you so much, Giorgio, for being here today and for your friendship all over the years. Actually, I must confess, I don't remember what your talk is about, but we don't care. Actually, whatever you're talking is good for us. Let me remind you, for the few of you who do not know exactly what Giorgio did, he has at least, I would say, 6 or 7 major breakthrough that would be a lifetime achievement for any of us. He has breakthrough in high energy physics. The Altarelli-Parisi equation is used to this day, and we are talking 1975 or something like that. It has been instrumental to validate the Higgs discovery, just to give you an idea. And it keeps being cited, I don't know, maybe over 10,000, I don't know. Is the P in KPZ, Kardar-Parisi-Zhang, which is a paradigm for growth phenomena in statistical physics. He has a very original solution of he has made a very original contribution to glass theory, spin glass theory, computer science, simulated tempering. I mean, it's unbelievable. So we are really very, very grateful to Giorgio for honoring us with his presence today. And I think I'm not speaking just for myself or for the organizer, but on behalf of the entire DSFD community. This said, Giorgio, thanks again, and I would say the stage is yours.
Okay, thank you so much. I am very honored by this introduction. You can hear me correctly?
Yes.
Yes, we can hear you.
Perfect. So I am very grateful to Stefan and also, of course, to Rosario to this wonderful introduction, and for maybe exaggerating just a little my merits. But anyhow, I'm very happy to hear that I'm well considered also as a human person, a human man. Now, let me come to the argument of my lecture. I would have been pleased to be able to give a talk on turbulence. Unfortunately, in the last week, I've not been working on turbulence in the last year, although I have tried to reflect on some problems, but have not done any serious progress in this direction. So I will give something like a general report on a different subject, which is related to not to spin glasses, but to real glasses. And now I come to let me try to show the screen. Okay. I think that it should be there.
Yes, yes, we see it very well. Thank you, George.
Okay, so one moment that I'm trying to put full screen. Now you still see.
Yes,
Okay.
yes, it's perfect. Yes.
Okay, fine. The title is Pebbles in Field Theory. I mean, the title remember me the book of Asimov, Pebbles in the Sky. But the idea is essentially that you can have marble, things like marble, glass, are very other substances that are nearly incompressible. And the problem is what happens when you put together under some pressure a large number of pebbles. I mean, if you're doing the experiment on the Earth, in presence of gravity, you always have some pressure. Only if you do on satellite you have zero pressure. Now, in the real world, the friction is very important. Now, in real material, you have a contact angle, which is 90 degrees plus minus delta, with delta that is not negligible for most of the common material. For some material, maybe 1 to 2 degrees, something like that. So this means that the force is nearly orthogonal to the surface. However, if you take a pebble which is done by marble over glass, the friction is small, and delta may be quite small. Of course, the one that you can see in this picture are not a spherical object, but of course it is also not convex object, but for convenience is much better that if we can consider spherical object. Now, the question that we can discuss, how the property of the material depends on the density, because if you put the pebbles together, if you slowly shake them, they tend to compress, and you have the phenomenon of slow compactification, which change the density, not of the single object, I mean the density of the whole set of pebbles. Now, this object will be in contact, there will be a network on contact, which will be the distance distribution, and which are the properties of the forces among different pebbles. Now, as I told you, it's better to consider spherical object, because for spherical object you can do a simpler theory, and now you can start to include some other features that are not considered a spherical object as a perturbation. Now, this is a real experiment. This is on the left, is a shaking machine. And you see that there are very nice plastic ball. The plastic ball are different colors in order that you can follow that more or less with some precision the trajectory when you shake as you shake in this case here. However, the plastic ball have a high friction among themselves. Now, the main idea of studying this kind of metamaterial is that we are exploring the statistical mechanics of macroscopic objects. For example, if you have spheres of a fraction of a millimeter diameter, we can easily construct a system up to million spheres that we can take on the top of our desk. And that is certainly some kind of statistical mechanical system. Now, you can shake this sphere. Shaking is something that corresponds to, in some sense, to the temperature, because the system is not at the minimal. And we can do experiment of this kind. We start in the high temperature region, I mean, in the strong shaking region. We cool the system, we decrease the shaking up to no shaking. And what happens? The final density depends on the schedule in which you shake. Now, the limit in which you don't shake and you don't have, and we have non-zero external pressure, I mean also very small, is the jamming point. This particle here stay at the jamming point. Now, the typical experiment, let me discuss an experiment that is done with sphere. This has been, you take in 150,000 spheres, and you make a tomography, you reconstruct the position of the particle, and the sphere have all the same radius, and of course you get some position of the particle with some sub-millimeter resolution. However, this is not quite correct because if you look to the position that are reconstructed, some spheres do overlap, which is not possible, but this is standard, always done in chemical reconstruction. You adjust by sub-millimeter the position of the particle in such a way that the system particles do not overlap. And therefore you have the data that correspond to post-processing. Post-processing corresponds to the original data at this green line here, while the red line is the post-processing, and the difference between the green line and the post-processed is only near to this peak here and can be seen here. This is just a technical problem. Okay, you can compute something like the correlation function. And now what happens is that if you look to the correlation function in the region which is very near, the distance between the sphere, the center of the sphere is very near to the diameter, you see that apart from a delta function at distance 0, there is some kind of singular behavior here, and therefore there is an increase of sphere that nearly touch, an increase of what you can call quasi-contact. If you take this from here, this does not seem too impressive. However, if you change the scale here, and we look on a log-log scale, you see that you have some kind of power, you have some kind of power behavior here, and you find that the correlation function becomes singular when the radius, when the distance between the particle are similar or equal to the diameter with some exponent. Of course, on the top of that, there are the spheres that are exactly a contact for which the radius, the distance between the sphere is equal to the diameter. But there is a strong abscess on a particle which are nearly in contact. And now this the problem that we may ask from the theoretical viewpoint is how can we estimate this power? Of course, this power is somewhat, at this level, is somewhat solid. It's been seen in many different types of experiments. And the idea that we can try to estimate this power here, to study this problem, is to consider, try to reconduce a problem within Boltzmann statistical mechanics. Boltzmann statistical mechanics is useful because there's been a lot of work that has been done after Boltzmann in statistical mechanics. And you see that if you have a zero friction spherical object, they are just half sphere. And the physics, the dynamics of half sphere is something that has been immensely studied in statistical mechanics with thousands of papers. Therefore, we can consider essentially now the problem of half sphere. Half sphere is something where you have Hamiltonian. The Hamiltonian is just a two-body interaction Hamiltonian. And for half sphere, the energy is infinite if the distance is less than the diameter, while the potential is zero for the distance greater than the diameter. Now, for some reason, we could also consider soft sphere and so on, but let us just stick to half sphere. Jamming is the point where the particles are in contact and they cannot move. So it's quite clear. This corresponds essentially to the infinite pressure limit of hard sphere. Now, hard sphere is easy to study hard sphere during the Via expansion when the pressure is small, but we want to study and now to understand what happens when the pressure is going to infinity. Now, one advantage of this formulation that we can do computer simulation for hard sphere. This is something that we know how to do, also large scale. And the computer simulation are very interesting because they overlap with the experimental data. Also, in computer simulation, there is, while on experimental data, you have always to discuss if there is friction or there is not friction. In a computer code, you write without friction, certainly there is no friction. And while in the experiment, you have the problem of reconstructing the position with high accuracy, it's clear that we cannot trim to have a real sphere and to know the position with the precision of a micron, not speaking the precision of Armstrong. And on a computer, we have the accuracy of the position with all the digits that we want. Okay. You see the screen, I would say.
Yes, we see it perfectly.
Okay, now it's full screen.
And also the full screen. That's perfect. Yes,
okay.
Thanks.
Okay, what I was saying that computer simulation are quite useful. I think that I don't need to explain you why computer simulation are important. They have a serious advantage of different kind. And if you take a hard sphere is a highly studied system. At low density, we can understand everything because we have the visual expansion. And the system of spheres have a finite viscosity and a non-zero diffusion constant. I mean, on the large scale, the sphere moves on a Brownian motion. If you increase the density of the system, the viscosity explodes, and it may increase by a factor of the 10 to the 6 or maybe more, and the diffusion becomes very small. Essentially, the diffusion becomes too small to be measured in simulation, and we stay in the glass phase. And we can discuss, if you look to one-time observable, for example, the pressure as function of the density, these do not show any irregularity. And anomalous behavior can be measured if you observe the system at two different times, which for last time differences, we look to viscosity. So roughly speaking, you may have something like, if we include the temperature for soft model and so on, you may have a region of the system which may be liquid, a low high density region where you may be gassed, and an infinite and the situation of jammed physics where the particles are really in contact, and you can arrive to different density depending for different cooling. Now, how this glass transition happens, we can discuss in a very qualitative way. Of course, there is more quantitative stuff to be done, and there's a lot of very quantitative ideas, but the ideas is very simple. I mean, it's something like when you stay in a subway or in other high density situation. At low density, it's clearly that you can move without any problem. At high density, you are blocked also because your neighbors are blocked. And your neighbors are blocked also because you are there. It's clearly that if in the subway you would be able to jump 2 meters up, remain there for 2 meters, dimension of cage in phase space, and also the single particle can move only in a small region. So you can more or less say that this is the phase space that can be reached by the particle. This is what happens that when nearly the gas transition, you stay in a situation where it's difficult to go from one region to another region. There are some entropic narrowing, and exactly as a gas transition, you stay in a situation that you are confined in your cage and you cannot move anymore. This is some approximation. Maybe you can take, it's clear that maybe you can take 2 centuries for go from one position of the in the subway to another position in the subway. But this is a very large scale on human scale. So for practical purpose, it does not mean too much to discuss if there are some really narrow tails from here to here. They are not. For example, if you take a typical glass material, the characteristic time of the material of the collision goes from 1 picosecond to a few days. Now it increase of the order of 10 to the 18, which is very huge increase. And of course, when the time scale is bigger than 1 day, it is very, very difficult to measure in a reliable way. Okay. Now, if you do now, you go on, you surpass the glass transition. After that, you go surpass the glass transition. You stay in a situation where the particles are confined in one cage, but they can move more or less. What can happen is the following. It can happen that you have the particle, when you increase the density, they become, you increase the pressure, they move smaller with increasing of the pressure, and the average distance at which they can move is going to diverge like the pressure to some power. And the other thing is that if you look to you try to form a singularity that I told there, and where there's a lot of an increased density of particles that are nearly compact. And therefore, at the nearly infinite pressure, the system behaves like the solid, and essentially you have this possibility of moving of the particle, which is going to decrease when the pressure is becoming larger and larger. Now, if you take a large scale numerical simulation, they are going to give you that this exponent gamma is the order of 0.4, and the value of this exponent k is the order 1.4. Okay, therefore, you see that you have something like exponent, and they are non-trivial exponent, and they are confirmed by a lot of simulations. The typical things that you were seeing in the numerical experiment was something order 0.5. However, this is much more precise measurement, and therefore you would like to make a theory, to construct a theory that is going to discuss this type of, to compute from first principle how this, how the particle moves when the distance is going to, pressure is going to infinity, how they become fixed, and which is the singularity of these things here. Now, one observation that is quite interesting, that contrary to real experiment, you can do experiment in a numerical simulation, not only in 3 dimensions, you can do experiment in 4 dimensions, in 6 dimensions, in 8 dimensions, and you can look how the average square distance behave, I mean, go to 0 when the pressure is going to infinity. Now, it's quite, you see that the data for different dimensions, they are nearly on the top one to the other. And just to give an idea how this, how much we are able to understand, to control the value of this parameter k, we see that if we take k equal to 3/2, the data are not well fitted. But if you take k equal 1.42, more or less the things is in agreement with all the data in all dimensions. So the point that we would like to, one thing that to understand how we can understand this type of features, because this type of features is quite impressive because they do not depend on the dimensionality. And okay, therefore, I think that we can do something. We can do something like okay, we know from experimental data and for numerical simulations that when we make a perturbation of the system in one point, when you are near to jamming, this perturbation propagates to a very, very large system. And that suggests that we stay in something like a critical region where the correlation length becomes very large. Now, if you analyze some approximate consistency relations and one do a end-wavered argument, one finds the two critical exponents are not independent from the other, and 1k is given by this relation here, which is the one satisfied by an experiment. The point that one would like to understand how we can compute directly the exponent. You hear me? Hello? Okay.
Yes, we can hear you, Giorgio.
Perfect.
Very well.
Okay. Now the simplest idea that we can have is to try to construct something like a mean field theory neglecting a correlation. I mean, mean field theory is in all the construction of theoretical physicists. The oldest one is the Curie-Weiss theory from ferromagnet, and what we that is the question that you've seen so many times for the spontaneous magnetization, where Z is a number of neighbors, and which is given for equilibrium lattice by twice the dimension. And of course, mean field theory is something that is approximate, but one could say that mean field theory becomes correct in the limit where the dimension of the space is going to infinity. So one thing that is maybe reasonable to investigate for some problem, the behavior of the system when the dimension goes to infinity. Of course, I know that this is something that has been tried by a few people to try to understand the behavior, for example, turbulence in dimension greater than 3, and in particular in dimension greater than infinity, but only a few papers been written for high dimensional turbulence. So really, we do not know if turbulence does simplify in higher dimensions, and which is the area when the dimension is going to infinity. That would be a very interesting question, but people try to discuss it theoretically, but numerically, you all understand that it's very, very difficult. Now, the first attempt at computation that we did on try to understand what happens in high dimension was done by myself and Zamponi, and give a result which was very bad, gamma equal to 0 and k equal to 2. Now, that the point that we do not get the exact result is something embarrassing, because because as we have seen, this exponent do not depend so much on the dimension. There was other numerical experiment that were done up to dimension 13. Dimension 13 is quite a dimension. And they gave always exponent in this range. So what realized that we are missing in what happened a theoretical point, that a possibility that happened in the system, and what people, these things that was discussed by people doing spin glass was people were calling Gardner transition. And what you can see here on the left is here on the left is the part that I described before. You start from the liquid, you cool the liquid, and you write a glass state, because the system breaks down in different cages. Now, however, what happens is that at a given point, you may have something like a Gardner transition, in which the cage starts to break in sub-cage, sub-cage, and after, when you arrive to the final situation, you have many jammed states here, and what happens that the system, when you cool, may go to one or one another or some other different state. Now it's clear that if this is what happens in reality, you have to include in your theory this possibility of formation of subbasing and sub-subbasing and so on. And you have to include the fact the phase space is completely different from this one, but it has something that is more or less a fractal configuration in fractal form. And now the picture is essentially the following. Here is what happens at the phase space. I mean, this is just a cartoon. The particle may move from one region to another one. The blue line is a region where they can move. When you increase the density, they are just constrained to move in one of this region here. But when you go on, you have some this basin here breaks in sub-basin. The sub-basin breaks in smaller sub-breaking, and you have this possibility. Now, this possibility is something that can be seen in numerical data and experiment, but as usual, it's not very clear if this is a sharp transition or is not. Now, let me just concentrate on the final result that one gets from the theory. Well, we can do we can do longer computation in infinite dimensions. Therefore, it's just a standard bona fide computation of mean field theory. There is some crucial point that makes the computation long and technically difficult. And we arrive to some exponent in mean field theory that, contrary to the exponent typical that we know of mean field theory, is something that are theta 42. Okay, the other exponent gamma that I was discussing before is very near to 1.2. It's 1.415 and so on. We have computed the 6 decimal place, but with some careful algebra, we can do 10 different, 10, 20 decimal cube. So therefore, this analytic computation and the fact that this exponent k here is you see, this exponent k is 1.42. It's essentially the theoretical value of the exponent. That is quite amazing because if you do the computation, this means that mean field theory is going to predict some exponent with a mole correction also in 3 dimensions, which is sometimes may happen, but sometimes does not happen. So the type of conclusions that we have some way get an analytic understanding on the German transition. An analytic understanding of the German transition is that we can do a simple model of statistical mechanics as sphere and infinite dimension. We can study it with the standard tool of statistical mechanics, and the standard, well, today's standard, because the tool we have to use are the same that have been developed for spin glasses 40 years ago, but after 40 years we can call them more or less a standard. And the appropriate mean field theory predicts the value of the measured exponent, both numerically and in simulations, in any dimension greater or equal to 2. Of course, there is discussions if there are logarithmic correction in dimension Z2 equal to. And what happens in the mean field theory predicts also the existence of this transition for a situation where the system is confined in one cage, or the system behaves something like the structure of the phase cage become fractal, and the correct value of the exponent can be obtained only if we consider this fractal nature of the phase space. And the result that we have some consequences on the theory of glasses, because of course they also describe what is this happens to glasses in the region of high density. Now, there's a lot of research that is going on. It's clearly that we have done many approximations. First all, we have used the field theory, mean field theory, and now if we use mean field theory, we know very well that there are corrections to mean field theory, and we have to compute the correction to mean field theory. Because one thing is to say, just as I told you, that what nice result. I did the computation mean field theory, and I found the result that are similar to the experiment. So mean field theory must give the correct result. And another thing that would be very important, if I could say, look, I computed mean field theory, I computed the correction to mean field theory, I found that the correction to mean field theory is small, therefore I have a good explanation, complete explanation under control that the numerical result should be, that the experimental result should agree with mean field theory. Now, the type of computation, this is something that we can do. This is something like compute correction to mean field theory and using the normalization group. But this is quite a complex computation that for the moment we have not done. Some other essential point that is very important, that we assume that the objects are perfect spherical objects. Of course, it's clear that experimentally we may have, especially if we consider ball by metal, the one that they use for real for industrial purpose, the sphericity is nearly perfectly spheric. However, in real world, we have some amount of sphericity. Now, if we have the system and not spherical, you have more than one degree. The degree of freedom, the effective degree of freedom, are not only translational, but they are also rotational. And And what happens that if we go very near to the transition, to the jamming point, the rotation degree of freedom are something that is very important, and you can do some work in which you start to understand first the spherical system. After you can start from the spherical system to add a small amount of sphericity and consider sphericity as a perturbation. And there have been great progresses that can be done in understanding this type of perturbation. So this is something that you can add. Now, the other things that you can add is obviously the friction. If you can study if you have a small friction. And of course, having a small friction is something that carries you far away from Boltzmann's statistical mechanics. But you can start to say, well, let me start from some configuration with the one that I get with neglecting friction, and to see if I do perturbation in considering the presence of friction. What happens is that both the presence of sphericity and the presence of friction, they make the system not critical, in the sense that there's no correlation lengths going to infinity, the exponent disappear, but you arrive to some region which is more regular. But however, it's something that you have under control. The other thing that is important is that you consider rheological properties. Rheological properties, it means you take the system, you add a strain, you take out the strain, or you may have the system, you can put a system of sphere between, I mean, it's something like in a pipe, as you do with water, and the water moves, and there is or the friction with the bundle, or you can put in a system with one boundary condition that moves in the with respect to the other one, and therefore all these objects may be put under strain with a constant strain, a time-dependent strain. And of course, also in this case, the introduction of strains carries you outside Boltzmann statistical mechanics. Sorry, when I say Boltzmann statistical mechanics, I mean equilibrium statistical mechanics, which means that the probability is exponential to beta h. Therefore, it's a non-equilibrium situation that is much more difficult, but it can be studied by considering these three quantities, sphericity, friction, and strain as a perturbation. The other problem that you can try to understand is essentially which is the type of behavior of the correlation or response function. This is something that in this case, if you look into these things here, you get something that becomes similar to field theory, like the one that's been used for Ising model. Therefore, you should find the correct formulation of the theory near jamming. And this is something that was, as I told you, is connected to the normalization group, and is some open problem that is quite difficult to tackle. Okay, so let me go to the conclusion. The conclusion essentially is that I mean, this is something where people say we, but not means we particularly. The problem of jamming has been discussed for a long time. However, the thing that we have discovered is not only that we have this jammed configuration, but there is a highly complex structure. I mean, this hierarchical structure of states, one embedded into the other one, this fractal structure, that is the same one that has been studied for spin glass, for the Edward Anderson model of spin glasses. So it's quite amazing that most of the technical, the results that have been derived for a completely different problem, spin glasses are managed with a mix of ferromagnetic and antiferromagnetic procedure, turns out to be the one used for half sphere. Now, the typical computation that we do with some kind of sophisticated mean field theory, because we have to, the computation are much more complex than the one of spin glasses. The tools are the same, but the computation is more complex, predicts the exponent that are more or less correct for 2 dimensions. Maybe with 2 dimensions there may be some deviation, and certainly for 3-dimensional system. The critical exponent in all 3-dimensional systems are more or less than 1% or the other 1% difference of the theoretical one. And we can say that also is quite important the fact that we have this Gardner transition, the fact that phase becomes fractal. And we have a numerical simulation and also experiments that have been done with hard disk confirm this picture. People takes hard disk, shakes this hard disk, and there's some agreement with the shaking hard disk with the numerical here. Of course, a completely open question is what happens on quantum half sphere, and the final conclusion that we are interested in half sphere because of the simple system that behaves as a glass, and this finding has been useful, it could be useful more to understand some of the features that we have in structural glasses. Okay, so I think that I finished. So thank you very much for inviting me, and I leave the floor to give back the floor to Sarah.
Can you hear me?
Yes, yes.
So thank you very much, Giorgio. I think I have a lot of questions for you, but I can ask them privately. It's really exciting. I see a number of connections with problems which we have been doing lately, but first of all, I would like to thank you again and to ask for a question from the audience. Giacomo, I don't know how to handle that, but I think people should raise their hand, right?
No, we leave them the choice to leave to lift the hand or to write on the chat. At the moment, I would have just a question, just a curiosity from my side, if possible. It was very interesting to hear this very inspiring talk, Giorgio. Thank you very much. And I was also considering some other materials that are closer to my research fields, like, for instance, paraffins, so on and so forth, that are that can be considered as glasses in their solid state. And they are also characterized by a complex transition, phase transition from liquid to solid with there is also a mushy zone that is an intermediate zone between with properties in between the liquid and the solid. And I don't know if maybe in your models it can be reassumed, this passage also in the passage from liquid to super cool liquid and to glass transition. I don't know if it can be considered similar, please.
Well, the point is that what we have done, I mean, we have done our computation, everything in something that is hard sphere. Now, the thing that have been a lot of discussion is to from hard sphere to soft sphere.
Okay.
After that, we understand we know that there are some regions where the things behave in a similar way. There are regions where the thing seems to work in a different way. But also the situation is soft sphere is not completely cleared.
Mhm.
And how much of the things survive. People to think there may be some region when you are enough near to our sphere, something behaves in some way. However, some other properties disappear, and so on. There is a lot of discussions on this point. And therefore, I think that the first thing to go in the direction that you're doing is to understand what happens to soft sphere. Once that we understand to soft sphere is something that we can try to extend to discuss to more complex material. The point you see that there are two ways that you can do, you can do theoretical physics. One way that you do theoretical physics is that you start to do phenomenological model, and you introduce something phenomenological model and so on. The other way that you can do theoretical physics is that you start on soluble model and you do perturbation on soluble models. I not say that one is better than the other. I think that we need all this type of approach. But for the moment, my interest is to fully understand the exact model, and to try to do and also the model that is better understood is the 3D, the hard sphere situation. And later on, and after there is all this work of doing perturbation with respect to these things, which is something that I know that exists, but are not really worked on computing this type of correction. Of course, one would have a clear picture for soft sphere, as I told you, one can go on and so on.
Okay, thank you very much.
Any further questions from the audience? Well, meanwhile, George,
there is a question.
Please. Let's give the.
Maybe I can ask to the question.
I don't know, Giacomo, are you managing?
Yes, it's Alexander Wagner. Maybe I can try to. No, he should be able to.
Alex, you should be able to.
Yes, I can speak directly here. So I have a quick question here, just a practical one. So typically we are looking at these polydispersed systems for simulations because otherwise in experiments, in numerical experiments, these systems crystallize. Now, in actual experiments, we don't need to do this. We can use spheres with a common radius. So I was wondering if the reason for that is somehow the friction that you mentioned in the very beginning of your system that somehow prevents the crystallization, and if including friction in your actual numerical experiments might get you closer to the physical experiments.
Yes, this is an interesting question. The problem is the things is the following. When you do the theory, you easily neglect friction. Sorry, when you do the theory, it's very easy to neglect the crystallization. You just do not consider the possibility the system is doing a crystal. When you do numerical simulations, you have various possibilities. One possibility is to use polydispersivity. And this you can do simulation with polydispersivity. Or the other things that you can do extremely fast cooling. If you do extremely fast cooling, the system will be entering the glass phase where the viscosity is near infinite and the diffusion is zero. And therefore, this is something that is important, especially in 3 dimensions. As you go in 4 dimension and a higher dimension, they also hard sphere do not really crystallize in time of simulations. The reason that they do not crystallize is essentially due to the following things. The structure of the liquid in 3 dimensions is not too different from the structure of the crystal. There is some differences, but it's not so different. When you go in higher dimension, something like 4 dimension and so on, what happens is that the structure of the liquid is very different from the structure of the solid. So it's much, the barrier for doing crystallization is much higher. Of course, there is no problem theoretically to do the computation with polydispersivity. It's just trivial to do, but you have to add the polydispersivity at the beginning, but that's easy to be done. While numerically, there is the people that are doing numerical simulations with polydispersivity, or numerical simulation with very fast cooling. I have done both of them, and I do not see any serious difference between the two as far as numerical simulation concerned. However, in 4 and more dimensions, everybody is happy with monodisperse stuff.
Thank you, Giorgio. Any further questions? While waiting, I have two very quick, Giorgio, myself, and then again, I will ask you in private. First of all, I didn't know that you seem to get very good results as soon as, once you take into account this Gardner transition, as soon as D is greater than 2. Did I understand correctly? Greater or equal than 2. Okay. At 2, there may be a few percent difference between the exponent, but which may show up as logarithmic corrections. Okay, so it seems to me that this is a huge improvement, because I mean the folklore was that mean field theory does not work other than in infinite dimension. This is no longer true. No, I mean mean field theory. If you look for the Ising model, which is the best understood model for statistical mechanics, we know that the exponent for mean field, we are speaking about exponent. Of course, there are 2 kinds of computations that you can do. One computation is to compute the position of the transition, and of course, the position of the transition in the real world is different for ferromagnets from mean field theory. The thing that you're interested in is in universal quantities like critical exponent and so on. If you look at universal quantities like critical exponent are given by Wilson are given by mean field theory exponent in greater than 4 dimensions, and in 4 minus epsilon dimension, they are given by the Wilson expansion, which is correct for small epsilon, and more or less gives a less than 1% value. You can compute 8 order, 7 order vectors, and so what happens in 3 dimensions. Now, the fact that the mean field theory arrives up to 4 dimensions is something which is dependent from the type of system. If you are doing the computation, for example, in the case of percolation, the upper critical, you have to do not a 4 minus epsilon expansion, but it's a 6 minus epsilon expansion. Therefore, mean field theory breaks in 6 dimensions. If you go to the tri-critical point, the liquid, or to the, anyhow, if you look to some special point for the liquids, not at a critical one, but the end point, or maybe it's a critical one, the end point of the liquid gas phase transition, the critical exponent works up to dimension 3. And therefore, you have a 3 minus epsilon expansion. So what we are not, unfortunately, as I told you, we are not being able to compute exactly the dimension at which you can start to do an epsilon expansion. The fact that the results are very good in dimension 3 and reasonably good in dimension 2
suggests that the dimension where you start to compute the correction may be something around 2 or 2.5, I don't know, but the one has to do the real, that is the part that we have to really do the computation. However, this is something that, however, this is a different, this is a different story. So what happens here that for some reasons, for this type of system, we have been very lucky that we find a system in which the correction to mean field theory are very small. Of course, it's not, let me add one thing. In one dimension, mean field theory does not work at all.
Well, that's understandable, yeah.
So the exponents in one dimension are very different from the one on mean field theory. So if we know that one dimension does not work, so probably they do not work also in 1 plus epsilon dimension. So there should be some dimension where everything breaks down, if we assume that everything is continuous in the dimension, and but unfortunately at the present moment I cannot tell you where. And I have most of the prediction from mean field theory and very good agreement also in dimension 2.
Okay. Thank you. And very quickly, I don't want to abuse, Giorgio, very quickly. At some point, you have the formula where the connectivity was twice the dimension. Is this just a detail? Because you can have different connectivities. You could have 2 to the power dimension. Is that an immaterial detail or that could change something?
Well, look, the connectivity, this is for the cubic lattice. For hypercubic lattice. What I mean, what is important is that the connectivity is going to infinity when the dimension goes to infinity. And I think that for all crystals that I can think of, the connectivity itself can go to infinity when dimension is going to infinity. So therefore, infinite dimension is related to infinite connectivity. And therefore, this is the reason that why mean field theory works, because if the connectivity becomes very large, the signals that arrive from the neighbor, each of the signals is small, and in some sense, what you have is something like the average of many signals that arrives, and therefore you can use central limit theorem and things like that. Therefore, mean field theory is essentially a central limit theory of the signal that arrives to some particle from other particle, and the correction to mean field theory correspond to consider the fluctuations to these signals. So every time that we have a lot, that the signal becomes very, very large, the number of signals that arrives, we get mean field theory. However, this certainly happens in the dimensions, because in the dimension, well, I don't know if you can do a crazy model in large dimension where you can solve by mean field theory, but.
Okay, no, but since we use many different lattices, but we will discuss that. I will ask you later on in private. So I think we have still time maybe for one further question from the audience before we leave Giorgio in peace somehow. Any further question? Giacomo, you don't see any?
No, I don't see any. I think that we can.
So I think we can at this point, thanks Giorgio so much again for his very and thought-provoking talk. Giorgio, I will come to you with many questions shortly.
Okay.
Thank you so much again for being with us.
Thank you, Giorgio. Thank you very much.
Thank you.
So I think that now we can have a coffee break. But before the coffee break, I have to tell all the speakers and attendees of the session in Sala Palma that the Zoom link has been updated, and so you should have received a new email in the recent hours, a few hours before lunch. And in any case, you can refer to the link in the website, the dsfd.org. So Sala Palma Zoom link has been updated. Please use the updated one. Now we can all have a very good coffee. And thank you, Giorgio, once again for being with us, for your very inspiring discussion and talk. Thank you very much.
Thank you very much. Goodbye.
Bye-bye. Bye-bye, you all. Recording. And we are, yes, on track because it's 3:50 p.m. So, good afternoon to everybody. I'm Giacomo Falcucci from the University of Tor Vergata, and we start the first session in Sala Leone of our DSFD 2021 with Alexander Wagner. He needs no presentation. From the University of North Dakota, and Alex is a friend. He is a faculty at North Dakota University, and he always helps us in organizing this DSFD. So thank you very much, Alex, for all your precious help always. And your work is what we can learn from mapping molecular dynamic simulations onto lattice gases, lattice Boltzmann. And you have 15 minutes, then we leave 5 minutes for the discussion. Please, Alex, the floor is yours.
Hey, thanks very much. Let me just share my screen here. Oh, come on.
You should be able, I gave you the...
Oh, it should. It's just my computer is being silly. Okay, now let's see if I can share my screen. There we go. Can you see my screen?
Yes.
Yes, it's perfect.
Excellent. So, now we have just a little echo here. Let me just close this off. Yeah, okay. So I want to tell you some more. I mentioned this during the last DSFD conference already. We talked about this project that we've been working on for a while, about mapping direct molecular dynamics onto lattice gases and lattice Boltzmann. So there we go. Oh, come on. Why is this looking so funny? Okay, so we can talk about. Okay, so this is the basic outline that we have. We can use molecular dynamics, and we've known this for a long time to model fluids, right? And of course, this is basically just solving Newton's equations for particles, right? And it's known that you can always do this, and you can look at any kind of problem that you can think of essentially with this, depending on the kind of force fields. So assume you have some kind of forces, and you have the positions and the velocities of the particles, right? And you can track all of them. The only difficulty with that is that it's expensive, right? And of course, the lattice gas was really a response to the difficulty of scaling these problems up. And the original philosophy of lattice gases was to come up with something that is not MD, but just conserves mass and momentum and has the right symmetries, right? That's the idea of FHP. And because you have mass and momentum conservation with this sort of minimalistic model, you can recover hydrodynamics, right? This is the original philosophy. And there are some issues with recovering it. There's some non-Galilean invariant terms in the incompressible limit that works quite well. It turns out if you allow, so the original model is allowed for exactly one particle per lattice direction. Now, if you allow an arbitrary number of particles, actually you recover lattice Boltzmann methods much better, which is a different subject that I won't talk about here right now, right? But you have the basic idea, you have just particles reside at some position X and T, right? And then they move from there to a neighboring cell in the next time step, and you follow these particles. And what you have to do is you have to kind of rearrange these particles with this Greek capital Xi, which is this collision operator. It's typically a probabilistic operation, and it conserves mass and momentum. And in doing so, we can recover in the macroscopic, so in the Boltzmann limit, we can recover continuity in Navier-Stokes equations. Now, these systems are very noisy. And originally, in order to describe this in terms of kinetic theory, you can take averages of these NIs, and you obtain this averaged evolution equation, which is the lattice-Boltzmann equation that we all love, which looks exactly the same as the lattice gas equation, except the F's are replaced, the N's are replaced with F's, right? Now this omega, however, it's a really different animal. The omega now becomes a deterministic collision operator. It's no longer probabilistic, and even though it looks similar, it's a completely different philosophy, right? And from this, you can derive your continuity equation and your Navier-Stokes equations, right? And that's a much cheaper way of simulating these macroscopic systems compared to molecular dynamics. Now, typically, well, you can derive a collision operator that exactly corresponds to what a lattice gas does, but it turns out to be advantageous to allow for some more freedom by basically imposing this local equilibrium distribution Fi0 and taking either single or multiple relaxation time approximation of just approaching that equilibrium, right? And you get a viscosity which has this lattice effect of this -1/2. It's like a lattice effect coming in. Now, one of the things that's kind of odd about this, which is something that you'll hear a lot more about in the next talk by Alexandra, is that this viscosity here becomes low if you bring, so if you put tau to up to 1, you bring it back to local equilibrium. If you bring tau close to 1/2, that means you over-relax, then you get very low viscosity. And that's actually the regime in which a lot of lattice-Boltzmann simulations are being used, but it's hard to justify that, but I won't talk much about that in this talk. Now, there is a lot of question about how to construct these lattice-Boltzmann collision operators, and in fluctuating lattice-Boltzmann, what the fluctuating properties of these systems ought to be. And the question is there a way of actually knowing what it ought to be from some first principles? Most of the approaches go, you take this approach, you derive the macroscopic equations, you see what spurious terms you have, and you try to fix those. But the question is there something more fundamental, particularly for things that you might not know in the first place, like what are the fluctuations in an interacting system supposed to look like? Which is not as, we don't have a good theory for that. Now, this was first introduced in this paper with Vesa, and I mentioned this in, I think, two DSFD conferences now. So if you want to know the basics of this, this is the sort of basic background paper of how this method works. Now let's go very briefly over this. The idea is then you have an MD simulation where particles move around according to Newton's equations. And you superimpose this red lattice where you say, well, all the particles that are in this red lattice, which is the central one that's drawn in, which is these green particles, they belong to this cell. And I simulate this for a time step delta t, and these particles evolve according to whatever Newton's equation tells them to do. And they end up, well, in some spread out region, which includes regions that are outside of this original simulation domain. And I identify these particles that move now with these lattice gas quantities Ni, which are particles that move from this cell to this cell above, right? We have this one particle here. There's two particles that moved into this cell, right? There's one particle moved up in this diagonal direction, and you can just count them up. And that way you can identify what these Ni ought to be. Now, once you've done that, you know what these Ni's are, and you can identify this collision term, which tells you how to rearrange them, and you arrive at this lattice gas evolution equation 12. The only difference is that you know the Ni's already, and the Xi I are now defined by the Ni. And you can just determine what they have to be to give you this system. And so if you knew a priori what the properties of this Xi I are, you would obtain a method that gives you exactly the densities that the MD simulation gives you. And if you had some statistical knowledge of it, you would at least get something that's statistically correct. Now, that's something that at least formally looks like a lattice gas, right? Now the question is, does this have anything to do with the lattice gas and lattice Boltzmann that we've been using, right? And so this is another example where you can look at this. You can take all your particles, they're all numbered. You can see as time goes on where they're moving to, right? You can just run the simulation and you can track where they are depending on your time step. So at the short time step, you have only maybe one particle, maybe two particles having moved, and there's more particles, and the longer you wait, the further they'll move out. And for very large time steps, of course, you have a very large possible set of places where they can move to, but in short times, they only move to the neighboring cells, right? And if you want to calculate that, what it takes is this expectation of the Ni, and you can look at this in a sort of average thing where you look at the probability of displacement of these particles. And if this one particle probability distribution is given to first approximation by Gaussian, you can analytically solve what this equilibrium distribution looks like. And well, as expected, so if your time step is very small, all particles remain in the original cell, and the longer you wait, more particles will move out, and they move out to the nearest neighbors, the next nearest neighbors, and then further on, as you go out, they move to more and more of these particles, right? Until they all get this distribution. You can actually calculate exactly, given that this is a Gaussian, what this thing looks like. Now the question is, does it have anything to do with these FI equilibrium? And it turns out, if you want this to be this FI equilibrium, so this is looking at U equals 0, this would be these three values that you have for the weights for the Lattice-Boltzmann. And they do, in fact, cross at one point, where this A squared is about 1/6. They cross, they're not exactly the same, because obviously there is a non-zero probability that particles will move further out, but they're really small, and so it's a very good approximation. Now, this is encouraging. The next thing you might want to look at what happens for different values of U. And you have, of course, the U dependence here of the F equilibrium distribution. And you compare that to the molecular dynamic lattice gas ones. And you see that for small velocities, they agree very well. For larger velocities, they don't fully agree. In fact, they do something very interesting, which is that the what used to be the rest particles completely converges with these moving particles, which has to be the case because this is a bit where in one time step, they're now changing position, right? So now your mean velocity becomes larger than 0.5, right? And now what used to be rest particles are the left moving particles, right? And the right moving particles. And you can see that at this edge point, they actually should be exactly the same as they have to be. And so this is not just a bug, this is an actual feature to make these lattice gases completely Galilean invariant, which these ones aren't, of course. And so I believe that this is actually a better way of doing it. Now, originally we did this to understand how to do fluctuations, because we're trying to develop these fluctuating Lattice-Boltzmann models, but we didn't quite know what the fluctuations actually ought to be. And we thought, well, maybe we can measure this. And this I already talked about, so I'll be very brief about this. This is this PRL, also with VESA. And the key result is that the fluctuations look like you expect from the ideal gas theory for a dilute gas, which is encouraging. But for non-dilute gas, you actually see something that looks very, very different, right? So these distributions don't even look like Poisson distributions. They're much wider, and that's a very interesting result. This is all focusing now on the Ni and on what happens to the total density. And you see here that there are large fluctuations. Now, one new thing I want to talk about here is I'll skip over those useful things here, is what happens if you look at the momentum, right? This is this new paper, also with VESA from earlier this year. When you look at, if you look at the momentum, so you have a lattice gas definition of momentum, which is just the NIV, the standard one that we always use in lattice gas and Lattice-Boltzmann. Now, you can also look at the momentum defined from Lattice-Boltzmann, right? So you have a lattice cell. Inside these lattice cells, you have, so this delta just tells you whether the particle happens to be in that cell, and it has a momentum that gives you another definition of the momentum. And if you compare these two, they're obviously not the same. Well, first of all, the lattice gas is discrete, right? You only get discrete values, so this is why you see these lines here, right? And also, of course, if you have one particle moving over over a boundary, you get a much larger value of momentum, whereas if a particle moves within the cell, that doesn't give you anything to the lattice gas momentum, so they can't be exactly the same. You see they're clearly correlated. But what's more interesting is the magnitude of them. So the slope is not this one slope that as you might expect. And in fact, as you coarse grain this, so go larger and larger systems, you see that this kind of curves over. And so this is a really strange observation, that not only the magnitudes are not the same, but in fact, which one is bigger and which one is smaller depends on the coarse graining that you have. Now, the lattice gas, of course, looks at positions at 2 different times, and the lattice pulse, the MD is an instantaneous one. Now, you could say, well, maybe it's about this time averaging, and you can define this new momentum, which is the time average momentum. We just take, well, you say, well, I'm just looking at the momentum in my cell over this time step and see how that correlates. And that is this delta T. And you see that they're similarly off. So they agree. So this time average momentum and the actual momentum, they agree very well at small times, because obviously this is just a finite difference derivative then. But they start to diverge at larger times, as you might expect, because these particles will move less if they diffuse around than you would expect just from their ballistic motion. But what's interesting is that
you have 2 minutes, please.
Yeah, that these things start to converge much more closely, and you can see that if you look at the correlation between these quantities here, the correlation. So this is, well, if this is 0, they completely agree. So for very small times, you have this agreement between this finite time one and then these. And the instantaneous MD one, whereas if you look at longer times, you see this interesting convergence of these particles. And you can see if you can describe this by theory. And you have this ideal gas, lattice gas theory, which describes what's going on reasonably well. You have obviously the flat distribution for the MD one, which the instantaneous time one is very simple. But the description of the time average momentum is more interesting. So if you assume that these displacements are independent, you get this dashed dotted line, which is actually a very poor approximation. But if you take into account correlations in displacement, which is what we had to do before when you looked at these fluctuations, you get a fairly decent description of these momentum correlations. Now, what's really strange about this is that at early times, these things do not agree. Now, the total fluctuations of the lattice gas are actually significantly bigger, almost like a factor of 2 bigger. And you can wonder if that happens on all length scale or not, because on the one hand, you might expect that these momenta agree, but it turns out that the fluctuations are indeed flat, as the ideal gas theory would describe as short times, but they're just much, much larger, because basically there's a discretization contribution to the momentum fluctuations. So that's the current fluctuations are much larger at short time scales. But if you look at larger time scales, something very interesting happens, which is that the lattice gas and this finite time scale things start to actually converge. You can see this, not only do the magnitudes converge, but even the spatial structures of those start to converge. And so let's get to our conclusions here. We can use these molecular dynamic simulations to define an exact version of lattice Boltzmann. And what you need for this is just the one particle distribution function for a particular molecular system. If you can find this function, you get out of that your lattice Boltzmann, right? We've seen that the equilibrium distribution actually agrees with standard LB for small velocities, which is the only place where standard LB is reasonable. Allows us also to predict the fluctuating properties of lattice gases for non-ideal systems, which are quite different from what was previously expected. Also, as usual, these fluctuating methods, they actually are more complex. They need more information. In fact, they need the 2-particle distribution function. And if you have the 2-particle distribution function, you can obtain the fluctuating properties both for the density fluctuations and for momentum fluctuations. And it also provides, and this is the subject of the next talk, which we'll hear about in just a second by Alexandra, the first principles derivation of the collision operator. And as Alexandra will show, it does show over-relaxation. And so all the properties of Lattice-Boltzmann have now been reduced to finding just the one particle distribution function of particles. And from that, you can derive everything you need to know about your Lattice-Boltzmann simulation. And with that, I thank you for your attention. And I'll take any questions that you might have.
Thank you, Alex, for this very interesting talk. We have room for a few questions from the audience. Are there any questions? I have just a curiosity, please, if possible.
Mm-hmm.
What about the computational burden of this procedure? The coupled molecular dynamics Lattice-Boltzmann. Molecular dynamics, we know that is usually quite computational intensive, while Lattice-Boltzmann is quite light. So, please.
So, what's important is, so this is a way of understanding Lattice-Boltzmann from from an MD first principles approach. It's not a computational method as such. It's really a way of obtaining some kind of first principle values for these Fi. If you do a simulation, of course, it's the cost of the MD simulation that limits this, right? So in fact, and then of course you have some additional terms, which is the cross graining. But what it allows you to do, it allows you to study what in first principle these Fs look like, and hopefully this is sort of where this is supposed to be leading. You can use that information to now devise a fluctuating Lattice-Boltzmann method or some integer lattice gas method that has the same statistical properties as the MD system, right? And you can use some of the things that you don't quite know how to do, right? Like boundary conditions, like multi-phase systems, like putting in the correct fluctuations for multi-component systems, right? And you can read out of your MD simulation what the corresponding Lattice-Boltzmann values ought to be. Then you should be able to import those and then run your Lattice-Boltzmann simulation with some of the parameters, which now you don't have to justify from macroscopic results, but you can
so like a fine-tuning
microscopic MD.
I see, like a fine-tuning of the properties. It's very interesting, really. Thank you very much, Alex. Other questions? Okay, if not, we thank Alex one more time, and we can go to the next speech, please. Pachalieva. Please. Alexandra she's a collaborator of Alex Wagner's, and please, Alexandra, are you here?
Yes, I'm here.
Okay, yes, we can hear you, please. Okay.
Okay.
Yes, so we also see very well your screen. Yes, please, the floor is yours. You have 15 minutes for your talk. At 13 minutes, I will tell you that you have 2 minutes left. Please, thank you very much.
Thank you. Okay, thank you very much. Today I will present to you how we derive Lattice-Boltzmann from molecular dynamics. This work is a collaboration, let me see, between me and Alexander Wagner. I'm a PhD student at Technical University of Munich. Currently, actually, I'm at Los Alamos National Laboratory as a graduate research assistant. And yeah, thank you very much for all the help. Here is an outline of my talk. So first, I will motivate why we're doing this. I'll show you how we go from molecular dynamics to lattice gas and Lattice-Boltzmann, which shows over-relaxation. And after that, I will show you like some details about the molecular dynamics lattice gas method. And then, since we want to look at collision operators, we need to have a non-equilibrium system, which I have been using simple shear flow. I'll show you the diffusive theory, some results, and discussion. So first of all, we don't know how collision operators really work. I mean, we have so many different collision operators, from just simple BGK to double MRT, or entropic lattice-Boltzmann methods, cascaded lattice-Boltzmann collision operator, cumulant collision operator. And I mean, as Ilya Karlin always says, this is like a zoo of collision operators, and we still look at them as a black box. And this black box, interestingly, shows over-relaxation. And this is also kind of like non-physical, as for now, it has been seen as numerical trick, which we're using to go to low viscosities. However, by using this molecular dynamics lattice gas tool, we can derive lattice-Boltzmann from molecular dynamics simulation, and that's actually showed as a lattice gas with over-relaxation, which is an interesting result. Okay, but what do we do? Like, how do we go from molecular dynamics to lattice gas and lattice-Boltzmann methods? As you know, molecular dynamics is an approximation of a real physical system where we have these Newton's second law equations. In lattice gases, we are having a fully fluctuating model, which is on a lattice. And by averaging this lattice gas, we can obtain lattice-Boltzmann method. And basically, in between, we scale bridge between molecular dynamics and lattice-Boltzmann method. So that's how we go through the system, and that's how we approach and obtain the molecular dynamics lattice gas approximation. And this is basically, as Alexander earlier mentioned, an analysis tool. It's not a full simulation method, but we take molecular dynamics simulations and we analyze their properties so that we can obtain better and more useful lattice-Boltzmann methods. Okay, a short introduction, because I will be talking a lot about over-relaxation in this talk. What is over-relaxation and where does it come from? So basically we have this, in lattice-Boltzmann method, we have this BGK evolution equation, and like usually Fi can immediately or even pass the equilibrium distribution function. And that's what, when it passes equilibrium distribution function, that's what we call over-relaxation. And in this plot, which I took from lattice-Boltzmann method by Tim Kruger, we show how under full and over-relaxation are represented. So basically, when we have over-relaxation, we overshoot past the equilibrium, and still we converge into the right solution. This is shown in blue, basically. Okay, however, this over-relaxation, as I mentioned before, is considered a numerical trick. And in general, lattice gases cannot show over-relaxation. Kinetic theory, as Bish and Ilya Karlin showed, they also cannot achieve over-relaxation from kinetic theory. So what is over-relaxation, and can we derive it from molecular dynamics lattice gas? And let me shortly introduce you to molecular dynamics lattice gas. I know Alexander already did that. So basically we have a molecular dynamics simulation, and we impose a lattice over this simulation. And then we track the position of the particles at every time step. So basically in this figure, you can see that the green circles are in times, like the position of the particles at time step delta t, or at time t, and the stars, the red stars, are the position of the particles in the next time step. And as you see, like they have moved in different directions depending on the physics we're simulating. And that's how we can write the evolution equation. And then the collision term is defined by this ni's, which are the particles, the number of particles which have moved from one position to another in a non-equilibrium system. And then after we average these properties, these ni's and the non-equilibrium collision term here, we can obtain the molecular dynamics lattice Boltzmann evolution equation as given below. So basically we can measure average properties of the underlying physical system exactly, and this can help us understanding lattice-Boltzmann method. Okay, since we're looking at a collision operator, and that's the most important thing we want to understand right now, we need a non-equilibrium system. And the simplest one we could think of is the simple shear flow. It's a symmetric system. We can average in space after Galilean transformation and in time because we have reached the steady state. And the linear velocity profile is also given by the shear rate. So basically everything of the system, like we know every small bits and pieces of the system. And to show you a little bit better how this is represented into a lattice, this is a local equilibrium distribution function. And here we see different layers of the shear flow. If you imagine this, the middle point is the central lattice, which I'm showing. The upper layer will be this one and the lower layer will be this one. And as you see, the probability distribution functions of the pre-collision will be given in this sense. Basically, we expect that the red line here will go a little bit further, but this system is close to equilibrium. And basically the collision or the pre-collision terms will look like that. So this is the FIs, which we're looking at from lattice-Boltzmann perspective. Okay, and since this, some dog here. Since we have a nice simple shear flow, we can find the diffusive theory for this flow, which is, yeah, I will show you that in a little bit later, like in the slides. But it's important that we need to find the FI. So once we find the FIs, our system, our MDC, molecular dynamics lattice-Boltzmann system is defined completely. And we know that we can find FIs from the one particle displacement function as given in the slide, where the one particle displacement function in diffusive theory can be defined as follows. We found this very interesting paper from 62, which describes this problem and gives this solution. So we have not derived it ourselves, but we use already published one particle displacement function. And basically this one particle displacement function, once we have it, we can fully define our FIs and obtain our collision operator as well. This displacement function, what it needs to be defined additionally are the moments. And first of all, we have used the diffusive theory, which was given in the same paper. And they're as follows. And then as we are doing molecular dynamic simulation, we can also measure these moments from the MD and also use these data. And later on, you'll see in the results how I compare these moments when we use them in this one particle displacement function. Okay, so I'm going to results right now. And basically, we were able to obtain all these moments, calculate the one particle displacement distribution function, the FIs, and then also the collision terms from the FIs. And then when you're thinking about a simple shear flow, we very much know that we can look at this collision operator as like two variables, omega alpha and omega beta. Because of symmetry, our off-diagonal terms will be basically symmetric, represented here in blue and red. And basically, this gives us one of our terms. So omega alpha will be calculated like that. And then omega beta is like a second freedom, like second degree of freedom of our collision, which is given by these green contributions here. However, the omega beta terms will be much, much smaller. So we are actually ignoring them for the purpose of simplicity here. And we look only at omega alphas because these are the much, much larger terms. From this, we calculate our pre-collision and post-collision terms, and we plot these. And I know this is kind of like a weird way of looking at the problem, but actually this gives us a very good idea where our pre and post collision stands. And here it's very important to mention that like our post collision terms actually change sign. And this is actually where going from under relaxation to over relaxation happens. And basically in the figure here, I'm showing you the M alpha and M alpha stars terms, depending on the time step of the discretization. And we have the results from the MD simulation, the diffusive moments theory, and the MD moments with multivariate analytical solution. And multivariate shown in red lines and dashed lines, and MD theory fit completely. And there is some interesting like displacement for the diffusive theory. And actually, if you think about it, the difference between the lines, so the red line and the red dashed line, that's actually the our collision term. That's how how large they are. Okay, so the change of sign, as I mentioned, at 1.6 is actually, that's somewhere here. It's actually corresponds to the transition from under relaxation to over relaxation. Okay, a little bit more results. How
we
the
have 2 minutes, please. Okay.
Yeah, how the relaxation time looks like. And this is like the relaxation time from the MD and the relaxation time from the multivariate probability distribution function with the MD moments. They have also perfect agreement. And again, here you can see that the transition happens at 1.6. And interestingly, the diffusive theory only has over relaxation. So our relaxation time is only equal to 0.5. We also plotted a simplified theory where the moments are, the X moment and the Y moment are equal to the mean squared displacement, and only the off-diagonal term or the off-diagonal moment is changing, and we see the same results basically. So this is like the key change occurs for the over relaxation in this moment. So that's the main important part. Okay, how do we understand under relaxation and over relaxation? Here we see this in ballistic regime, we have always under relaxation. And basically we have pre and post collision, which are in the same sign. So in pre and post collision terms, we have going towards equilibrium or passing equilibrium. Whereas in diffusive regime, we have different signs of the pre and post collision terms, as you should see it here in red and blue, where the pre-collision is going towards equilibrium and the post-collision is passing through equilibrium, and that's how we achieve over-relaxation, actually, this zigzag effect seen before. So we think that in diffusive case, because of memory effects, because of the loss of the memory effects, we have over-relaxation, where in ballistic regime, collisions are rare and particles carry a memory of their history over large distances, and we see under-relaxation there. This is just an exaggerated sketch, actually. And to conclude this talk, we have derived the collision operator for simple sheared system. We have measured over-relaxation from lattice gas and lattice Boltzmann methods. More details about this work can be found in this archive paper, and future work, we want to know the true form of the collision operator. We can use machine learning to obtain that. And of course, we can look at different physical phenomena. And thank you very much for your attention, and I'm open for questions.
Thank you very much, Alexandra, for this very interesting talk. Are there any questions from the audience? Is there any comment that you would like to add?
Myself, or I don't see anyone right now.
So Alex, if you like, considering your previous.
Just for a detail, I have the work is very interesting. Yeah, just out of curiosity, I will need to read better the papers, but maybe I lost the detail. What about the viscosity?
So the viscosity is fixed in our case right now, but actually the viscosity in a way changes depending on the discretization of our system. Yeah. So when we're going from smaller lattices and smaller time steps, we have a lower viscosity, like effective viscosity. And when we are having larger discretization, larger lattices and larger time steps, because we actually fix the ratio between the time step and the lattice size in order to conduct this study. And basically for smaller discretization and time step, we have smaller viscosity, and for higher, we have higher viscosity effectively. But actually the MD simulations are conducted in the same, they're the same density basically, and thus viscosity. Yeah. Okay.
Is there a dependence on this choice for the diffusivity of the particles, for instance?
What do you mean?
The how fast they spread. Are they always?
So
I mean, the diffusion coefficient.
I think the diffusion coefficient will also change depending on the discretization, because then the more time you have, the further your particles will go, right? Yeah.
Oh, okay. Okay.
But the MD system is fixed, so that's what I'm trying to say. That it's really the discretization is making all the difference.
So it's like, I mean, it's because of a coarse graining effect in a sense. So you're going to have something like an effective diffusion coefficient that depends on the finite size effect of the discretization. And correct. That's what I was trying to, whether there are corrections to a simple scaling of the diffusion coefficient with respect to the discretization. That was more or less. Okay, thank you very much.
I hope I answered, yeah.
Yeah, no. Thank you.
Okay, thank you very much. Let's thank one more time, and we have just a few minutes for a very quick coffee break. Then we come back in 10 minutes here and start the final afternoon session of this first day of DSFD 2021. So enjoy a quick coffee and see you soon. Bye-bye.
So that they could be able to, in a very short amount of time, simulate, for example, the unsteady loads on a full-scale airplane or off-design conditions such as icing or even airframe nodes. But what you might not know is that, in fact, even fully compressible lattice Boltzmann method have been used in the industry since 2014 in order to simulate transonic and supersonic conditions on real-scale geometries. But the main issue with these approaches is that usually they are not all the time more efficient than Navier-Stokes Fourier solvers. And this is the reason why people that have been working on this solver, they have kept looking for a better trade-off in terms of robustness, accuracy, and efficiency in order to replace Navier-Stokes Fourier solvers on a larger number of applications. The question is then, how do we do that with lattice Boltzmann method? And in order to understand that, let's come back to the methodology that is used to design lattice Boltzmann method. So the first thing that we do usually is that we choose a set of macroscopic equations that we want to recover with our lattice Boltzmann method. Then this set of macroscopic equation, we translate it in terms of equations over the moments of the Maxwellian. Once we have this set of equations in terms of moments, then we can use either quadrature methods or moment matching approaches so that we can choose the right discretization of the velocity space so that our lattice Boltzmann method will be able to recover the proper macroscopic behavior. So when it comes to Navier-Stokes Fourier equations, if you want to do this based on the Gauss-Hermite quadrature and using only a single distribution function approach, then you will usually end up with approximately 100 discrete velocities, which is rather inefficient for industry-oriented simulations. So one way to improve the efficiency of your code is to move towards a two-equation methodology that will basically decouple the evolution of the density and momentum from the evolution of the energy using two different lattices. And you can even go one step further by replacing the second lattice for the temperature evolution by either a finite difference or finite volume scheme to discretize the energy equation. And in fact, you could even go even further by relying on correction terms and then ending up with only 20 equations to solve at each point of your simulation domain. And if you look at what has been done in commercial solvers for supersonic flow simulations, this is exactly what is done, for example, for similar power flow solver that relies on 39 discrete velocities and a finite difference approximation for the entropy equation. And for Pro-LB solver, they prefer to rely on correction terms so that they could further decrease the size of the lattice. But then you need to be extremely careful when it comes to the way you compute the correction terms so that you do not lose too much accuracy. And in fact, accuracy is one of the, even though these approaches, these hybrid approaches are extremely efficient, they usually lack accuracy. And this is the reason why recently similar power flow is coming back to a double distribution approach in order to improve the accuracy at higher Mach numbers. So at the end of the day, if you look at models that are used in the industry, they all rely on analytical equilibria and static lattices. And in the rest of the presentation, I will focus on two less common alternatives that will allow us to get also a pretty interesting trade-off in terms of accuracy, robustness, and efficiency, which are namely the use of numerical equilibria and adaptive lattices. So in order to understand what's the idea behind the use of numerical equilibria, let's come back to that sketch. And here what we do is that with the numerical equilibria, we will numerically enforce through iterative procedures the moment matching approach so that we can get more physics with the same lattice. More precisely, let's assume this form for the discrete equilibrium populations. Here we have lambda coefficients that are called Lagrange multipliers and that are computed iteratively through a root finding solver that will impose a number of constraints that will depend on our moment matching approach. And in fact, the number of constraints, we can choose it in an arbitrary manner so that we can exactly impose the targeted physics of interest. The interesting thing about this approach is that it has been introduced about a bit more than 20 years ago for supersonic flow simulations based on Latigar's cellular automata. And even if it has not been used again after this paper, it has been extensively used for discrete velocity models in order to simulate hypersonic rarefied gas flow simulations, such as atmospheric reentry simulations. And in these approaches, what people usually do is that they only use 5 constraints that correspond to mass, momentum, and total energy. And they only impose these 5 constraints. But when you look at the corresponding macroscopic equations, you can clearly see that there are numerous errors that appear because you are not imposing enough moments. And in order to compensate for that, these approaches usually use pretty large lattices. But since we can choose the number of constraints in a rather arbitrary manner, we could simply impose the full set of 26 moments so that we could exactly recover the Navier-Stokes Fourier equations. But since you are relying on a root finding solvers, the more you add constraints, the more the solver will have issues to converge. So you will have issues to compute the equilibrium functions. And if you have issues to compute the equilibrium functions, then you will have stability issues. So a good way to have a solver that recovers the good physics at a lower cost is to find a good trade-off by using, for example, the pragmatic approach that was proposed 20 years ago by Letalec and Perla, and which mainly consists in imposing in an exact manner all the convective terms, even though we still have some issues with the remaining diffusive fluxes. These errors are likely to become smaller and smaller as the Reynolds number will increase. And we showed that based on this approach, in fact, it's sufficient to use only 39 discrete velocities in order to get the full monatomic behavior of the Navier-Stokes Fourier equations. And by further relying on the approach proposed by Dubrovka and Miosans in 2001, meaning using a second lattice in order to get the proper polyatomic behavior, then we are able to end up with a good trade-off in terms of efficiency, robustness, and accuracy. And in fact, this has been confirmed by simulating 1D Riemann problem, the supersonic flow past a 2D NACA airfoil, as well as the supersonic flow past a 3D sphere. But let's focus a bit more on the results obtained with the 2D NACA airfoil. For this particular test case, we also evaluated the performance of our code, and we showed that even by using, say, 78 discrete velocities, we were able to obtain performance that are similar to 3D Navier-Stokes solvers. And by further relying on GPUs, we were able to get a speed up to 100. So this is pretty interesting because this is also the kind of speed up that you can expect from weakly compressible lattice Boltzmann method. And this can be explained here by the fact that even though we rely on an iterative manner to compute the equilibrium, the number of iteration of the root fighting solver is approximately in average of 2, which is rather small, and it can go up to 4 iteration when we get closer and closer to the stability limit of the model, which is here a Mach number of 2. So if we want to further increase the stability of our model, we can further rely on adaptive lattices, meaning lattices that will adjust to the macroscopic quantities of the flow. So in order to see why we need to do that, we need to remember that the velocity distribution functions, in fact, they are very different shapes depending on the local flow conditions. And if you want to recover all the changes in shape of these velocity distribution functions, usually you need to rely on very constraining best practices that have been proposed, for example, in the context of discrete velocity methods, in order to ensure good properties in terms of stability and accuracy. So at the end of the day, using these practices, you will need hundreds of thousands of discrete velocities to get the correct physics for large variations of density, momentum, and energy. And this is the reason why these people, they propose to reduce the number of discrete velocities by looking at local variations and adapting the lattice accordingly. And in fact, this trick to adapt the lattice to the local variation is rather old because it was proposed once again in the 90s, even for the 27 lattice by Nadiga. And more interestingly, it has been already used in the context of the lattice Boltzmann method, either to recover the physics of Euler equations or the Navier-Stokes Fourier equations. And when you look at recent adaptive lattice Boltzmann method, you can clearly see that the only thing that changes is the way we reconstruct missing information. And in fact, recent approaches can be divided into 2 families. Families that require space interpolation and iterative streaming step to get good results, and those who do not require either space interpolation or iterative streaming step. And by performing a very simple comparison, we can clearly see that in order to obtain an efficient and accurate scheme, it's better to stick to the original strategy proposed by Sun in the 90s, meaning no interpolation, no iterative streaming step, and simple reconstruction of missing population. But the question is then, how do we construct interpolation-free adaptive lattice Boltzmann method? In fact, one way to do that is to rely on integer value lattice shifts, meaning that you will center your lattice on the mean velocity at a macroscopic level. But in order to do that, you need to be sure that at a given point in your simulation domain, two different versions of the lattice, shifted and unshifted, will be able to coexist in terms of stability domains. And we showed in our paper that if you rely on standard polynomial approximation for the equilibrium, then you will need to have at least 81 discrete velocity in 2D in order to get something stable. But by further relying on numerical equilibria, we can use only 21 discrete velocity, which is the 2D version of the 3D model that I've been talking about just before. So now that we know how to construct a stable interpolation-free adaptive LBM, there is still one question, which is how do we compute missing information at the interface between two parts of the simulation domain where we have two different lattices? And in fact, it's not that complicated because this is basically the same problem as the one that you are facing when you are dealing with boundary conditions, meaning that you could use non-equilibrium, the extrapolation of non-equilibrium. You could use the moments directly of the population as it has been done by Tim Reyes and his co-workers, for example, or you could use the decomposition of equilibrium and non-equilibrium parts. And in fact, in our work, we prefer that last option because it does not depend on the lattice and it is extremely efficient. So there are several ways to compute the equilibrium part. You could use either analytical or numerical equilibrium. And for the non-equilibrium part, there are also several ways to do that. You could use the Chapman-Enskog expansion, but in that case, you would need to discretize the time derivative of the equilibrium part, meaning saving data at previous time steps, which is not a good idea from a memory footprint point of view. So instead, what we prefer is to rely on Grad's formulation of the non-equilibrium population, which at the end of the day only requires the knowledge of equilibrium population and velocity and temperature gradients that can be evaluated through second order finite differences. So by doing this, we are able to propose an interpolation-free reconstruction strategy that can be coupled with any kind of equilibria, even though in the rest of the presentation, we will focus on those that are based on numerical equilibria. In addition,
we have 2 minutes, please.
Yeah, okay, thank you very much. In addition to that, as I said, this problem boils down to the same problem that we are facing with boundary conditions. So we can use the same reconstruction technique to improve initial and boundary conditions. And this is what will be done in the rest of the presentation. So when it comes to the validation of the proposed approach, we first started with the propagation of different kinds of waves, shear waves, entropic waves, and acoustic waves in inviscid conditions with a relatively coarse mesh. And we did it for different velocity, background velocities up to 3. And as you can see here, we end up with pretty nice results in terms of dissipation, numerical dissipation and numerical dispersion. In addition to that, we can clearly see that the scheme has pretty good isotropic properties. Moving now towards a bit more test cases that are a bit more complicated and that include discontinuities. Here we show that by simulating Riemann problems in either 1D or 2D, we were able to obtain pretty satisfactory results, even in the inviscid case, with only negligible impact on the accuracy. So if we look at the 1D Riemann problem, we can see that results obtained with the standard approach and with the adaptive lattice almost lead to the exact same results. And looking at the 2D Riemann problem, we can clearly see that even if small oscillations appear close to the transition between two different lattices, at the end of the day, we obtain results that are pretty satisfactory. And to me, the most important thing is that even by relying on a pretty naive way to compute the equilibrium, the numerical equilibrium when it is missing, meaning that at the intersection, at the interface between two lattices, you need to reconstruct the equilibrium. And to do that, you don't know what are the values of the Lagrange multipliers. So what we do here is that we reset these values, meaning that we reset the rule fighting solvers, meaning that we will increase locally the number of iterations to converge toward the equilibrium that we are looking for. And even by doing that very naive approach, we only divide the performance of the code by a factor of 2, meaning that by using something that is smarter, we would only lose like 30 or 40% of efficiency. So this leads me to the conclusion of this presentation, which is that the use of numerical equilibria allows us to get more physics with a given lattice, because we are able to impose an arbitrary number of constraints, whatever the physics, as long as this number of constraints is smaller than the number of lattice of discrete velocities that you have in your lattice. In addition to that, by working with interpolation-free adaptive lattice-Boltzmann method, we can end up with a very accurate and efficient lattice-Boltzmann method that do not need complex collision models. Here, we only use a BGK collision model with, when required, shock sensor technique. And this approach did not need to decrease the CFM number nor the time step in order to get stable results. When it comes to ongoing work, we will further improve the performance of the proposed approach by reducing the size of the lattice. We could also use our reconstruction strategy in order to select part of the simulation domain that will run using only 19 discrete velocities, as it is done, for example, in PowerFlow software. All of this will be done in the context of GPUs, since now Palabos is running on GPU, as it will be detailed by Jonas later this week. And this will allow us to properly compare all the compressible lattice-Boltzmann method that has been introduced in the literature during the past 20 years. And one interesting perspective would be to also see what are the results that are obtained in a rarefied gas flow regime, and how do the proposed approach compare to DVM, DUGKS, or DSMC. And last but not least, recently there were some papers were published regarding compressible lattice-Boltzmann method, and they showed that there were some very nasty mode transfer that were appearing depending on the proposed approach. And this can be identified by simulating a very simple convection of a vortex. And as you can see here, after one characteristic time, there is a very nasty pattern that appears on the temperature field, whereas the pressure field remains correct. And by running that kind of simulation with recently proposed adaptive lattice-Boltzmann method, we were able to show that these approaches were also suffering from that kind of mode transfer. And the question that I'm trying now to answer is, are all compressible lattice-Boltzmann methods suffering from such a mode transfer? This concludes my presentation, and thank you for your attention, and I'm open to questions.
Thank you, Christophe, very much. Merci beaucoup.
Thank you.
For the presentation. So, are there any questions from the audience?
There is one question regarding the performance of the of 3D simulation with the proposed methods. In fact, I can tell you that for the 3D sphere, we got the same performance as for the 2D Nakai R4. When I say same, it's approximately the same. There might be small discrepancies in terms of a couple of percents, but that's the same order of magnitude.
Okay. And then another one, is there any node, no particle for the adaptive lattice strategy? The reconstruction step will introduce numerical noise, I guess.
In fact, it introduces numerical noise. It's just that it's rather small. As I said, I think on the Riemann problem, you can clearly see in 2D that there are small oscillations, which is normal because you are locally changing the numerical scheme. And if you locally change the numerical scheme, then you introduce numerical noise.
Okay. Just a curiosity, if there are no other questions in the meantime, did you evaluate your scaling up performance with the GPU?
Not yet. In fact, I was supposed to do it, but then we decided to, because this is a CUDA code, we decided to record everything in Palabos. And since Palabos was not yet on GPU, that's why we waited for almost a year before doing that. But we intend to do it. Kartik, in fact, one of my co-authors, will do it doing his PhD. Okay,
I would like to suggest you something, if possible. We have just published a few works with extreme flow computation. You will see them, my presentation on Wednesday. And maybe it would be interesting to quantify the performance, the computational performance with the scale up, starting from your CUDA code, then with Palabos, and then with our hybrid CPU GPU, which is CUDA Fortran, basically.
Okay.
And we have used a supercomputer here in Italy, Marconi 100, and we have quantified all the performance. So it would be interesting for, I think, for both of us to share and to compare because we have done basic tests with, for instance, the lead-driven cavity, for instance. And I think that we can directly share this one, the performance. Can you hear me? I see you. Okay, frozen. Okay. And then we can refer to some more sexy cases that we have done separately. Okay. But I think that it could be, I will also talk to Jonas, and maybe we can arrange something interesting for the next, very next future. Okay.
Yeah, for sure. This would be very interesting.
Okay.
Can I have another small question?
Benedict. Ciao, Benedict.
Hi, how are you?
What is yours? Fine.
So I have one question about temperature. So your adaptive lattices are shifted, that's fine. Integer-wise, also fine. But how do you deal with temperature constraints? And in the end, I'm aiming at the question of how much do you actually increase the Mach number range? So what's your limit? Because if you don't scale temperature, you will still run into stability issues at large temperature ratios. So I'm guessing the solver is still like limited to Mach 2-ish, something around that. Is that right?
So yeah, you're totally right. So in the paper, we precise that for these test cases, in fact, the temperature fluctuation remained pretty small. When I say pretty small, I mean that the ratio between the maximal and the minimal temperature was below 3. So we didn't have to modify the temperature. So you could also modify the length of the discrete velocity depending on the local temperature.
Sure, but then it becomes very tricky to fit it on a lattice, right?
Yes, this could be depending on the streaming step that you are using. In fact, this is one of the tricks that I have not talked about that is used in some commercial solvers. You are not forced to use exact streaming step. Anyway.
Exactly. And also, I mean, since you're saying it's interpolation-free advection and so on, I mean, you still rely on basically a reconstruction by finite difference of the gradients, which is, in the end, a similar thing than interpolation, right?
Not really, I would say. Because the main issue is that when you introduce errors at the level of populations, it's very difficult to anticipate what will be the error levels at the macroscopic level. Do you see what I mean? Or
not quite, because you also do this by reconstructing the non-equilibrium part. And I'm also wondering, because non-equilibrium in theory should be Galilean invariant because it just depends on gradient. Why do you have to reconstruct it like you do at the moment? You can just take it, right? Because if you don't consider temperature, then this should be fine as is. No?
I'm not sure to understand your question. So you said that the gradients are Galilean invariant, yes. But since we are reconstructing populations in the local reference frame, we know the formulas.
Okay, I think I mean something different in the end, but I think we can talk privately.
It was also quite my presentation was quite dense, so no problem at all.
I think that you can add some few details maybe later with Benedict.
Yeah, sure. Okay, thank you very much.
Okay, I think that unfortunately the next speaker just told us a few hours ago that he could not come today, so we have a little pause before the final plenary session with the Professor Koumoutsakos. So if you would like to continue this discussion for another 5 minutes, no problem. If you need more time, maybe you can use a little bit more, you can be more comfortable to share details through email with Benedict. Okay, Christophe? Okay, are there any other questions from the audience? Okay, so let's thank Christophe one more time, and let's wait a few moments for Professor Koumoutsakos to come here to end this very interesting first day of DSFD 2021. You can have, I think, a little coffee if you need another one, because we have 10 minutes, and we will come back at 5:20 p.m. Okay, see you later. Bye-bye. Okay, good evening again. I am very proud to tell you all that we conclude this first session of DSFD 2021 with a plenary speech by Professor Petros Komoutsakos. Petros Komoutsakos is Gordon McKay Professor of Computing in Science and Engineering, and he is a faculty director at the Institute of Applied Computational Science of Harvard University. He is an incredibly solid track record in fluid mechanics and in applied physics with the study of soft matter and also artificial intelligence, bio-inspired robotics and computing. And I am very happy that he agreed to join us for the DSFD. And I really thank him very much once again for joining us. Please, Professor Komoutsakos, you have 40 minutes, but the schedule for you is totally free. So thank you very much. The floor is yours.
Okay, thank you very much, Robert, and thank you very much to all the organizers for giving me the opportunity to present in this lecture series, in this DSFT conference. So I understand that you are meeting also in person, or you're meeting, or is it all virtual?
Only virtually, unfortunately. Unfortunately,
Yeah.
only virtually. We planned to make an hybrid version, but this year too, we are just online.
Okay. So I was gonna say that I stand between you and some good Italian food, but maybe that's not the case. So let me start my talk. So as you can see here from my talk, I have put the words A and I, but this is not about AI. This is about angels and insects. And what I'm talking about angels and insects, I'm talking about two different things. I'm talking about the way we think about fluid dynamics and the way we think about things that are flying and they're very powerful. And we also have how nature is making things that are flying. So the insects is the way that have these imperfections by nature, and the angels perhaps is the way we are thinking of what should be a super flying entity. So I wanted to juxtapose these two things and talk about nature and artificial intelligence in fluid dynamics. It's kind of a personal talk. I would like to give you my personal journey in this field that started a few decades ago, and I would like to show you what are the latest things that we are pursuing these days. So talking about fluid dynamics and the exploration of fluid dynamics is very important. So one of the insects that I used earlier, they are very powerful in the sense that they have survived more than 200 million years because they were able to have wings, and then with the wings, then you can utilize the flows for surviving. So the flying, of course, has been very fascinating by humans, and it's a wonderful thing. It's particular when we get these possibilities. We observe flying in such close and detailed distances, like this one here. There's some videos that have been taken by David Lentic. And of course, we always wanted to fly like the birds do, and the person who tried to do that, the pioneer of that, was Otto Lilienthal, who was also German. And then after this picture was taken, he crashed and he said sacrifices are necessary. So today we have technologies, in fact, that are able to let us fly and to let us do very interesting things. So there is new technology that perhaps can advance the way we are flying. And we are trying to use these technologies into some of the existing machines that we have. So there was something that came up a few decades ago about how to put all these micro machines onto aircraft. This is back from 1993, but the problem in any of the technologies that we develop as humans is that, yes, they look wonderful, but when you look at them in practice, you can imagine that these micro machines, they may have problems to fly, and they may have problems in rain, wind, and debris, and all these kind of things. So what we need to do is we need to have technology, and at the same time, we need to optimize the utilization of technology. So the question is, how do we go about taking some of these fantastic technologies that the engineers make and then incorporate them into our devices? So it's classical to go about and to learn from nature. And that's why you see a lot of great people in fluid dynamics, because we tried it once and we failed dramatically. But at the same time, the Italians, they painted this thing very beautifully. So trying to learn and to imitate from nature, doing it one-to-one may not be the way to go. So another way to go about this is to either learn from the final products of nature, or to learn from the algorithms, or what we perceive as algorithms that nature is utilizing to solve problems. So there is ideas like this that you can observe in nature, and at the same time, people are thinking very creatively. They are thinking of having all sorts of different wings combined with existing wings. But a little bit more seriously, I would like to tell you how people have been thinking or have been thinking about incorporating natural technologies in some of the projects that I was involved. So the first project that I was involved was motivated by this situation. Back in 1993, there was an Israeli Air Force F-15 that was involved in mid-air collision, and you can see this video on the that I will show you in a second. This Israeli Air Force was able to land the F-15 without its wing.
We couldn't see each other, and we collided. Big commotion, big bang, A4, basically fireball immediately, and I found myself with maybe 30 degrees.
So apparently he was able to land the aircraft without even with losing the single wing. So he's landing this thing, and actually he said that if he knew that he had lost his wing, he would not have been able to land it, because he would have been about that. This led to some programs that actually went in at Ames and in the US for some time, where the idea is to use self-repair in flight control systems and try to use neural networks in order to that would learn and be able to control some of these machines. So back in 1997, I was at the Center for Turbulence Research, and then there was the group of Charles Jorgensen that they were actually using machine learning neural networks, even before a lot of people talked about neural networks, in order to do control for some of the aircraft that people were studying. And there was a particular project that I was also involved where my name is not up here. But we were basically looking at doing tests in the wind tunnels at NASA Ames, and instead of testing every single angle that would be possible, the idea was that you train a small neural network, and then instead of doing all the experiments there, then you are able to interpolate in between to find for different angles for the drug. So this combination of fluid mechanics and machine learning, again, this was a time that it was back in 1997. Actually, when I was doing these things, a lot of people at the Center of Turbulence Research were telling me, why do you do these things? These things are obsolete and they have failed. And in fact, actually, people in fluid mechanics always had some kind of an aversion to artificial intelligence. And one of the people actually who was responsible for this aversion was James Lightfield himself, who came up with the Lighthill report.
The overthing of the longer term of computers. The scientific community has a heavy responsibility to put forward its carefully considered view of the facts to avoid the public being seriously misled. Just as the US National Academy of Sciences did in 1966.
In short, basically, he was thinking that because you have to tell the computers a single that you had to then he said that this would be an intractable problem with a combinatorial explosion of possible solutions. So actually, the Lively report was responsible for the AI winter in the UK, and I think it had some bearing to the AI winter in other parts of the world. The interesting thing is that one of the things that Lighthill was attacking was speech recognition, and it's interesting to see that there is actually speech recognition right here, and these are the captions that are being automatic from his speech.
Enormous sums of money have been spent.
So that's why you see, instead of enormous sums of money, you see normal sums of money. So AI does make mistakes, but I think it was a bit exaggerated what happened back then. And at the same time, there was a pushback from the computer science community towards the fluid mechanics community, and the computer science community would say for some time, like, who the heck is Lighthill? He was just a researcher in fluid dynamics, where it is easy to be misled by complicated differential equations involving continuous variables, something that does not exist for computer scientists, and are non-existent in solarized solve. So, of time heals a lot of divides, and we are arriving today where we see that artificial intelligence has become a big thing. And there are people like that think that this is our final invention, it's the biggest existential threat. And there is also others that are a little bit more modest that say it's AI, it's transformative, it's the worst or the best thing that ever happened to our civilizations. We just don't know. So now there is another pragmatic view that talks about artificial intelligence, and that's actually a view that is adopted a lot in finance. There is a great book which is called Prediction Machines, and it's the simple economics of artificial intelligence. And basically what these people say, where others see transformational new innovation and hype and all these kind of things, the main argument that they have, these people, is the reason that we have artificial intelligence today is that simply the price of computing has fallen. So the idea is that computers have made arithmetic cheap. Solving complex equations is done more easily and in less time. So the idea is, what does AI technology make cheap? Prediction. And therefore, prediction is central to decision making under uncertainty. So better prediction under uncertainty, new opportunities for all companies. So the math and the economics are quite clear. I actually believe that indeed the computing is something that has made artificial intelligence to be very attractive. But at the same time, I would like to argue that computing alone is not enough. And so the examples that I will give will bring some of these ideas into perspective for at least my thoughts about artificial intelligence in fluid dynamics. Now, computers have been amazing, and here's my personal history with computers, and then over the course of the time that I have been doing research, an undergrad in Athens, using a VAX to today, I think actually this number now is not only 100 billion X, but it has been 1 trillion X. So we had some tremendous technologies, and with these tremendous technologies, what we have been doing, and us and others, we can look down at the nanoscale and look at waters inside carbon nanotubes. This was supposed to be the mesoscale, where we are looking into blood flows, but we don't see them here. For some reason, my keynote doesn't want to show the blood flows. But we have also been looking, I hope it will show that, we have been looking also in the macro scale, where we are studying things like flow structure interactions. And shock bubble interaction. So the computers are indeed very powerful machines. There is a multiscope that allows us to go from 10 to the -9 to 10 to +9, if you like, if you think about astrophysics. And so that's a unique capability. Now, at the same time, there is a lot of questions as to what is artificial intelligence and how. So yes, we have computers, but what is artificial intelligence? So there's a lot of definitions about artificial intelligence. There is the definition of Bellman about automation of activities, rationality, acting like humans rationally. There is one definition that I like very much and which actually blends very well with the ideas of computing. And it comes from one of the pioneers of artificial intelligence, actually one of the persons that was shot down by Lighthill, John McCarthy, that says intelligence is the computational part of the ability to achieve goals in the world. So the idea is that you are looking for a system, and what you're trying to do is whether the system is trying to achieve a goal or not is not part of the system itself. It is the relationship between the system and the observer. And so whatever a system having a goal or not, the way you observe very often nature, for example, the goal is not necessarily a property of nature, but is the relationship between nature and us. So how do we observe this particular system? And then when we try to understand a particular system, like nature, for example, or we try to predict a particular system or control it, then sometimes we try to do that mostly from the outcomes rather than understanding the mechanisms of how the systems are working. So this is very important to understand here and to make a pause, because very often in fluid mechanics, we are very much interested in mechanisms, and we're doing large-scale simulations because we're interested in mechanisms. But nevertheless, in the approach of the artificial intelligence, what you care is you care more outcomes, you control, and not necessarily what are the mechanisms by which you control. So going back to computers, again, computers became the public care from computers when they beat Kasparov in the chess match. And today there's more and more news that are coming about computers beating us in all sorts of different things, to the game of Go, and even beating us in the game of poker. And so this idea of how do you go about solving problems when you're solving problems in the context of artificial intelligence, I would like to use this example here, where you have a little animal encounter a problem, probably like the problem that this pilot encountered when it lost its wing. It was something that he has never encountered before. So this animal here is trying to solve the problem. So he is trying some solutions that he knew. Then he's trying a new solution that may look right, but you can see here that it's totally missing the point. But the thing is, by keep going by this trial and error, then he does the computation, and eventually he figures out, or she, to solve So the question is the intelligence, and there comes the definition of artificial intelligence is to achieve goals. So we may think that this thing has some kind of intelligence, but then again, he did all these things by trial and error. Is intelligence trial and error? Now, artificial intelligence is computational ability to achieve goals. So here's other examples. There's these insects here that are able to fly and to land. There is other examples where there is fish that can stay behind a certain place. And then I will talk about some of these things. You have some fish that you see them swimming in tandem. So we are thinking that they are trying to exploit each other's flows. But again, they are achieving particular goals, and what are the goals they are achieving is an important question. I had one more slide here, which I don't understand why it disappeared, but let me quickly look for it, because that's an important slide that probably I deleted inadvertently. Just give me 1 second to look for it, because I wanted to show you what are the capabilities that computing has today. And I just don't know if I will find it in a second, but anyway, it doesn't matter. But basically, I wanted to communicate that what we were able to compute back in 1997, what would have taken us, let's say, 3 minutes, would take us a year. Now it basically takes 3 minutes. In any case, the types of computing that we're doing. So there's 2 types of computing in a sense. So one type of computing is we use the computer to execute our instructions. Other type of computing is to try to instruct the computer to achieve our goals. And then we are leaving some kind of a freedom to these machines in order to achieve goals. So the goals that we may have is how do we go about optimizing, how do we go about doing dimensionality reduction, and of course, how do we go about predicting, how do we go about controlling, which are all exercises that we do. So I would like to discuss some of the approaches that we have had over the years in these different domains. So on learning to optimize, as we said, we hear about the output of a system and not necessarily the interior of the system. So we're treating a lot of problems with output relationships. And the idea was that you have black boxes, and the black boxes are all the different flow solvers that you have or the different experiments that you may have. And the question is, if I want to perform an optimization, is there a way that I can find out a probability distribution that contains my optimum points? So the story is that as I sample the parameter space, I'm trying to use the data that I collect as I am sampling different locations in the parameter space. And from these locations, I select the points for which solution win over other solutions. So I'm constructing a probability distribution of good points. Usually we use a Gaussian probability distribution as the candidate probability distribution. And therefore we have a technique called covariance matrix adaptation, ES. We are treating the flow solvers or the experiment as a black box, and we're having these input-output relationships. And by changing the parameters of the problem, we try to construct this probability distribution. Now, many of the things that we do in fluid dynamics is very expensive. So I've been using actually meta models in order to replace the extensive evaluations there in the section process. So these are we were doing about 15 years ago, and more recently we have been using this thing to discover objectives for nature. So you have here a little animal, and the little animal, when it is disturbed, is escaping in a particular way. And the particular way it's escaping to the right is that it's bending its body in a C shape. It doesn't escape by moving its tail as a normal fish will do. So you try to understand why this thing is happening this way. So what you do in this context is you don't care about understanding mechanisms, but you specify a cost function, which is how far can I escape. And then you do the optimization, and then you find that indeed this particular C star is an outcome of the optimization. This is the cost function. This is the number of simulations that it takes you. So it takes you hundreds of simulations to arrive to this result. But then the interesting thing is that this is where the reverse way of doing flow physics is entering. Instead of studying flow physics and try to figure out how can I optimize the motion of the body to take advantage of flow physics, what you do is you optimize and then you try to understand the flow physics. So the flow physics that we understood over here is that basically what happens is we are looking at Lagrangian coherent structures that are helping us to delineate what happens in the flow structures. So we have seeded some particles in the vicinity of the body at the beginning of the movement of the body. And then what you see is that this guy, basically by doing the C star, is trapping the fluid. And by trapping the fluid, you trap a certain momentum, if you like. So he traps the fluid, and by moving its tail, it generates a vortex. And this vortex is taking away all the fluid that it was near the body. So it's almost like you're in a boat, and the boat has some rocks, and then you throw behind some rocks, and then the rocks are pushing you forward. These little animals, what they do is they trap fluid, and then by generating vorticity with their tail, they're pushing away the fluid. But then this is the physics that we learned after we did the optimization. We cover experimental results, but it's the reverse process that I was interested in doing. We have applied these things in many different fields, and now a lot of people are picking up this covariance matrix adaptation to study things also in laboratories, and going from ultra thin mirrors for things that are going to space to optimizing flapping fish propulsors in the lab. Now, another thing you can do from nature is to do dimensionality reduction. I was telling you that I was participating in the programs at NASA Ames at the time of doing neural networks. And I was introduced to neural networks was by a guy called David Rumelhart. David Rumelhart is the person who invented the backpropagation. So he was teaching a course on computational psychology at Stanford, and I had the opportunity to take it and learn from David Rumelhart. Of course, at that time, I was always wondering, what's the big deal about backpropagation and all these kind of things? This is just all chain rule of differentiation. But nevertheless, we all know that this thing became very, very popular. Now, at that time, what was popular in fluid mechanics was the proper orthogonal decomposition for analyzing the flow fields. The proper orthogonal basically is looking for the eigenvectors of a particular covariance matrix. You can actually formulate this problem. The respective thing that you do in neural networks, you have some input, you're processing the input, and then you're getting an output. Here, you see the POD specified in a particular cost function, and then we take this cost function, we specify a particular form for a matrix, and it's a linear matrix, and then we're solving a linear eigenvalue problem. So this is very mathematical. It's a particular way of doing dimensionality reduction. Now, the neural network way may look a little bit surprisingly, may look completely unrelated, but I will show you that surprisingly the two things are very much related. So when you do this transformation, what you can do is you can actually, you find the error between the data and the output of your model, and then you minimize to find out what are the weights. But now, the thing that becomes very interesting is if you have input and you are asking the neural network to reproduce the input. So you're going through a constriction over here, and then you're going to an expansion again. And then when you're doing this exercise, actually, if you allow for the activation functions to be linear, then you can show that the proper orthogonal decomposition was actually recovered by equivalently having neural networks. So a neural network with linear activations, and by specifying the latent space to be equivalent to the number of vectors you would have kept if you were doing proper orthogonal decomposition, will give you the same. Now, the powerful thing about the neural network is, this is work by Baldi and Honig. Now, the powerful thing about the neural network is that now you don't need to stay linear. You don't need to go only through this linear algebra, but you can do now nonlinear principal component analysis. So this is actually, in fact, something that we introduced back in 20 years ago. I remember it took me a long time to be able to publish this paper because we were showing that neural networks were better POD in reconstructing flow fields. And we were showing a systematic way where you can go from linear neural networks, which were actually equivalent to the POD, to nonlinear neural networks. So actually, these were, in my opinion, some of the first time that someone actually did deep neural networks. And we did deep neural networks because it was just paying by trial and error. And we discovered that having shallow neural networks, we were not getting good representations. But actually, here's the plot that I wanted to show. So at that time, 20 years ago, we basically at some point stopped doing these things. And the reason we stopped doing things is because they were so expensive. So back in 1999, I wrote a review article about applications of machine learning algorithms to flow modeling and optimization that was published in the CTR annual research briefs. And they were actually very generous for allowing me to write that there, because there was a lot in artificial intelligence, all these things there. But I saw where computers stood at that time. So this is the top computing capabilities we had. And very recently, well, last year, we wrote another paper with Steve Brandon and Bert Noack, where we reviewed machine learning for fluid mechanics. That seemed to be much more well received from what I did 20 years ago. But the difference basically is the following. In whatever we would run, and it will take us 1 year to run in 1997, today it takes 3 minutes. And in my opinion, that has made a big difference. So it doesn't mean that there is no intelligence in what we do. In fact, actually, what is important now to note is that now we just simply have to take the computers into account, and we just have to think different in conducting machine learning research in fluid mechanics. So we have been doing that, and among the different neural networks that people are using, there is one particular type that I cared very much, and these are recurrent neural networks, because I felt that they are very important for unsteady processes that we have in fluid mechanics. So I like to, I will not spend, so they are like classical neural networks, except that now the data you have, they depend on time. And so you don't want to have classical neural networks where the input at time t is affecting the output at time 1, but you want to have some hierarchy in time. Now, the problem with these neural networks is they're not converging. They had an issue with the vanishing gradient. This was solved by something called STM that I will not spend a lot of time, except that is the thing that makes Go work and Google Translate work. But I want to show you how we apply these recurrent neural nets in trying to predict certain systems in fluid mechanics. So the idea is that what we do is we have a particular system, and then what we do is we have, together with MSubsys, we have introduced something that is called model. But the interesting thing about neural networks is that they tell you that you try to predict the future by using some time series of the quantity of interest from the past. And there's actually a theorem, there's the Tarkin's embedding theorem, that gives you some reassurance that such an issue would work. So one of the things that we try to do is we try to actually combine the recurrent neural network and mean stochastic model that gives you some information about the statistics. But now, so here is an example of what we did. So we took a Kuramoto-Shivasinski equation. At the Kuramoto-Shivasinski, it's important to look at the hyperviscosity coefficient, because as hyperviscosity coefficient becomes smaller and smaller, then you get finer structures. So what we took data from DNS of Kuramoto-Shivasinski, it's 1D in space and time, and that's in space-time that you see here. And then what we did is we tried to look at the principal component analysis of this, and we tried to see how many modes did we need in order to be able to reconstruct this particular flow fields. So what we did is, instead of learning, so what we wanted to do is we wanted to collect some input at the beginning of this flow, at the beginning of the XT diagram, and then to see what we can predict at a later time by using the data only at an earlier time. So we didn't try to, we forgot that we have Kuramoto-Shivasinski. We use the Kuramoto-Shivasinski data early on. But then what we found is when we tried to do that by using the complete information, this was not possible. Instead, what we found that was very useful is to learn SVD. So you do a singular value decomposition of this field, and then you are learning from the early times of this particular states. And then the idea is to use this kind of things as training data. So I will go back to this to see, I don't know why it doesn't show this thing. So the idea is the following, and I'll play the movie afterwards. The idea is the following, that you are learning up to the yellow lines on the SVD, and then you have to go back, then expose it back by increasing the matrix, by padding it with zeros to give you the full field. So you will see three predictions, a prediction at about half the time corresponding to the amount of time that we had done the learning, double the time or equal to the time of learning, and then taking it to about 3 times from the time of learning. So this is the yellow is just right after learning. What is this? This is the dark red, let's say, and then the pink and the orange is progressively increasing in time. So what you see is like yellow, yes, you're doing a very good job. I don't know why it's doing this to me. If you go to the orange, what you do is not so good anymore. But if you go to the pink, which is a little bit later, well, actually going to the dark red, it's still good. Going to the pink, it's becoming also a little bit worse. And then finally, when you arrive at the orange down here, you're starting to fail. But nevertheless, I think this is a good behavior. The story is, I want to show you that these things also, they are good at predicting. And if you're having a relatively low coefficient, a large coefficient, then you're predicting quite well. But a lot of people in machine learning, they're showing only successes. So here I want to show you also failures, because the training, when you start to have very small values for you, so the hyperviscosity terms, they become very important, or in a sense, the nonlinear effects become very important, then we start to lose it. And there is articles like this that came out, and actually they were referring also to our work, that machine learning amazing ability to predict chaos. And I would like to stress that machine learning actually is not able to predict chaos to the best of my knowledge and to the best that I know from our work. It's good, but I think we still need to do some kind of thinking. Another thing I want to say about machine learning, and I would leave it at that, is that the way that you do the training is that's what depends on what you're going to be getting. So you're very much dependent on the data that you're using. So there is this example of detecting an elephant in a room. They have a room where they're able to train a neural network to recognize people, laptops, chairs, all these kind of things. And then they randomly throw the image of an elephant in there. And then as soon as you start to do that, then the neural net is not able to recognize even if someone is a person or someone is a laptop. So some of the objects disappear. Some of the objects, they have different names, just simply because they will recognize that the elephant, but then it will be able to say whether something is a chair, and it will not depend on the elephant in the room. I will hurry up a little bit to move part of machine learning that I'm quite excited about more recently. And this other part came from our efforts to try to learn to do control and to learn to collective swimming. And one of the hopes that I had was to try to put robots and fish to swim together. So there is another type of learning, which is called reinforcement learning. And the idea of reinforcement learning is that it's not supervised, that you know what the answer is. So in that sense, a bit more flexible from the previous example that I presented. And the idea is that you have some kind of a stimulus action pattern, and you get rewarded if you behave in the right way. So this is actually a place where this thing was pioneered, was at Harvard by Skinner, where he actually trained pigeons to play ping pong, and he trained the pigeons to play ping pong by giving them reward every time opening it. Here, there's a gate down here that has food. Every time the ball crosses in the other side, then whether one gets to eat some food, learning to play.
Two ping pong table. One pigeon pecks the ball as it comes toward him and knocks it toward the other pigeon. The pigeon pecks the ball back across the table. If it goes past one pigeon,
Professor Koumoutsakos, are you there? I cannot see him anymore.
Can you hear me?
Now I see. Yes. Now I see you again. Okay, I lost you for a few seconds.
So have you seen the pigeons playing?
It was just a static picture. It was just a static picture, like a photograph, not a movie.
Okay, I start again. So I was talking about reinforcement learning, and these are the key elements of reinforcement learning. And I was saying that the place, one of the points where first these things were observed was by the group of Skinner here at Harvard in the Department of that he was trying to teach pigeons to play ping pong, and
the two pigeons are at either end of a small ping pong table. One pecks the as it comes toward him and knocks it toward the other pigeon. Other pigeon pecks the ball back across the table. If it goes past one pigeon, the other pigeon can eat, and if it goes the other way, the other pigeon can eat. But there's a real game. The pigeon is reinforced for a cross-court shot if that is what gets the ball.
So the idea is that this thing has a long history. It has a history in psychology, mathematics, in dynamic programming, in economics, in computer science, and very recently it has actually achieved some remarkable successes. It's behind a lot of successes in computer science, on the Atari games, on some of these benchmarks that you see here, on the chess and Go and in games like that. So in fluids, it has been a little bit more recent. So there are people who have done work in 2016. There are people, I think this is Luca Biferale did some things in 2018. And there's also Reddy and others who use some reinforcement learning in order to fly. So these are things that we started actually back in 2010 or 14 was the first paper we published, where we were teaching some of the swim in circles. They actually had a paper where we taught some kind of dipoles to learn to collaborate and to fly together as swarms by holding particular points. And this was a very interesting thing because they're very strong interactions. There is 1/r type of interactions between them, but by doing the game many, many times and by having each one of the agents follow a particular point, we were able to get eventually to stay and to do different trajectories. And I will be showing you two examples of how actually we got reinforcement learning for swimming. So learning is very similar to dynamic programming, except that you are again having some kind of a stochastic process. So you're having an action and a state where you're observing the environment and you're taking some action. And at the same time, you have some kind of an expected utility that depends on the states and the action that you're taking. But what you don't have is you don't know the explicit formulations of F and C and R here. You have only the capability of sampling them. So that's what distinguishes reinforcement learning from dynamic programming. And that's what makes also computationally expensive. So you can sample, but you don't necessarily know these particular functions. Here, you can have a black box interaction, or you can know everything, but it's not going to help you because I need a way for something to advance your system. So the idea of reinforcement learning in more mathematical terms is that you have to environment, observe some states, you have to take some actions, and then you have to receive some kind of a reward. And the story is come up with the policy here for us is a recurrent neural network that we are getting some kind of an input, and then as an output, the mean and the variance of the probability distribution that defines your policy. So the idea is, can I use experiences that I make in order to identify time histories and identify how to behave over time so that I can achieve certain goals. I feel that I need to, so we have developed several algorithms for that. And the algorithms that we developed, actually, we them to be, the specific algorithm we developed, we found them to be better than algorithms that you would find over. And actually, many of the algorithms that work in artificial intelligence in terms of rewards, they don't work when you apply the fluid mechanics problem. So there is a certain importance in algorithms of our own, but I'm not going to talk about these algorithms. I'll show you, I will not show you artificial intelligence problem, I'll show you some of the results. So one of the, I wanted to see whether we can train a fish to maintain a position behind an obstacle that is shedding. So what we did is we have a self-propelled swimmer, and then the self-propelled swimmer, he has some information about its relative position and the angle of the obstacle, and then it can change its undulation amplitude. And then what we ask the swimmer, please stay within this box. You should not go very close because you cross. So, and then what we found is we wanted to minimize the swimmer's energy output. Okay, so the state was where you are, the action is your undulation, and then you want to minimize your energy output. So indeed, we found actually that the swimmer is able to learn to slalom between the different vortices and to maintain this particular position. So you can say that this was kind of a success. By the way, this is unpublished, so I'm showing you because this is indeed unpublished. So I want to show you the issues that these things have. So you train the swimmer to learn to stay behind an obstacle at Reynolds number of 1,000, and then you tell him, okay, now with what you learned at Reynolds number of 1,000, let me now increase the velocity, the flow. So now you have to swim at Reynolds number 1,200, and the swimmer is able to do that. But now you go and you increase the Reynolds number to Reynolds number of 2,000, and you will find out actually that what you learn for Reynolds number of 1,000 is not sufficient for the swimmer at Reynolds number of 2,000. So generalization and reinforcement learning requires further work. So also what we found is that sensors, or what you are sensing, if you replace the location by sensors and all kind of things, depending on the type of states that you're choosing, you may get complete failures. So the whole balance of how to choose action states, etc., is a very delicate issue. We have taken this and we have applied it to the case also of swimmers, that if you want one swimmer to follow another swimmer, how do you go about doing that? So you have two fish, and then you want to have the front fish swimming as it pleases, and then the other fish behind. The idea is how can you maintain the motion of this fish so that it keeps a particular distance, or basically it takes some advantage of the flow field. So we specified two different rewards. The first reward that we said is, okay, there's the first fish behind, and then there's the line where it travels. And then we asked the fish to be able to stay on this line. So indeed, we found actually that when the fish behind stays on this line, then we found out that actually it's using less energy than the fish in front. So the fish in front is swimming in undisturbed flow. The fish behind is very disturbed flow because of the vortices, but is able to manage itself in such a way, because it's line, so that it profits and actually is using less energy. And now we said, okay, what if you now have another situation where we ask you to be efficient? So this fish could swim anywhere, actually swims right behind the other fish, and is able to take advantage of the vortices. So there is structure interaction here. And then by taking advantage of the vortices, it's able to use the energy. We took these examples and then we took them in 3D, and we said we cannot afford to do simulations in 3D to learn in 3D, but let's use the two-dimensional lessons that we learned, and then we put the three-dimensional fish one behind the other. By the way, the simulations here have been done with remixed vortex particle methods, and they use adaptive mesh refinement and all this kind of multiple bodies. This could be another separate talk. The thing that I want to mention here is that when you go to 3D, the flow behavior is different from 2D. And in 3D, the vortices actually are not right behind the swimmer in front, but the vortices are to the left and to the right. There's all these vortex rings. So training a swimmer to swim right behind the other one actually has no energetic benefit. And in fact, you can see if you look at it, the cross section, all the vortices are on the side, all the energy is on the side. So it's actually you should be swimming in order to extract energy from the swimmer in front. So we did that, and again, I'm mad of how exactly we went about doing all these things. But now here is actually optimal situations for swimmers, where the swimmer is able to swim in such a way so as to harness the vortices from the swimmer in front. And you can do it also in other situations here, because the front swimmer is producing two vortices. The best situation is you have two fish that is taking the flow and this is and takes advantage of them. And of course, the best scenario is that you have two fish in front, and it's actually that out in such of a complicated vortex field, this fish here is able to harness and extract a lot of energy from the flow. As I close, I want to tell you a more recent idea that of how one can use reinforcement learning that I am excited about. And the idea that I would like to describe very briefly is that so far, reinforcement learning has been used to control. And think about it, what is control? Control is that you have the equations and then you add a term to the motion of the body in order to control the flow. Now, if you go to the modeling of that we do flows, for example, let's say you're doing an LES simulation, and then you're doing an LES simulation, and then you add the subgrid scale model, which in a sense can be seen as a controller. So the idea that we had, and this is a paper that came out in Nature Machine Intelligence about a year ago, the idea that we had is, what if we have the grid points of the simulation, not only grid points, but also to be agents that are learning. And what are they learning? In this particular case, you can formulate that the grid points, they're solving the Navier-Stokes equations, and at the same time, they are learning to find the closure.
Professor Koumoutsakos, are you there? I think we lost you.
Do you hear me now?
Okay, yes, now I see you and I hear you. Yes, yes.
Did you see this slide?
I just are you sharing the screen, because I just see you?
I'm sorry. You're absolutely right. You see now my screen, correct?
Yes, yes. Now I see. Yes, we were looking at this slide and you were commenting it.
So again, concept here, I want to convey the concept, not the details. The concept here is that you have a grid and you use the grid to solve large eddy simulation runs, whatever you have. You don't do necessarily DNS, okay? And then the grid points, in my view of this multi-agent scientific reinforcement learning, as we call it, is that the grid points are also agents. And they are agents that are talking to each other and they are sharing their policy. And when they do that, what you try to do is you try to train these agents, which is actually the grid points. The grid points have a dual role. On one hand, they're utilizing the equations, and on the other hand, they are learning to find the subgrid scale modeling by communicating between each other as to the state of the flow field. You have to train this thing with some kind of a DNS data, and the hope is that what the subgrid scale model has been learned can be generalizing to other Reynolds numbers. So here we did DNS of homogeneous turbulent flow, and then we train the agents to a flow at a Reynolds number of 111. And then this is the energy spectrum, usually the energy spectrum way around, but Guido wanted to have the energy spectrum with a K on the y-axis and the energy on the x-axis. And basically you train on the Reynolds number of 111. You see that even when you train, you're not able to capture the solution of the DNS. But what we found is actually we're doing as good as the dynamic Smagorinsky model. And then when we are actually took it and we tried to exploit at lower Reynolds numbers, we always did as good as the dynamic Smagorinsky model. But then as we started to push into higher Reynolds numbers, we found that we were rather reasonable. Dynamic Smagorinsky model, I think in some cases, right under our curves. But again, you start to lose it, and you start to have to lose in accuracy. The results were quite encouraging. Another thing we're doing more recently, and again, this is unpublished work, we have been thinking, since we can do the Smagorinsky model for LES, another thing we can do for LES is we are training now the multi-agent reinforcement learning to learn wall models for LES. And the idea, again, is the same. You have grid points in the wall region that are learning from the flow field. I will not discuss all the details, but what we find actually is that we are training for a channel flow at Reynolds number 2000, 4000, 8000, and we were able actually to get some pretty good results, even for much higher Reynolds number. And even when you train for channel flow, you are even able to generalize to a turbulent boundary layer and capturing the friction coefficient for different Reynolds number. So you're training on a channel flow and you can capture a turbulent boundary layer. I would like to close. I spoke too much, and I would like to tell you some of the things that I have learned on all this artificial intelligence and machine learning over the years. I think learning implies finding an algorithm that is effective for the problem to be solved. And that does not necessarily imply machine learning. I think finding, using the human brain and the human thinking and the education that we have been having all these years to solve the problem is very, very important. And it would be very unfortunate if all the new generations, they go into machine learning, and it starts to become very difficult to find anybody who knows how to do proper numerical analysis or numerical methods. So I think that's something we need to worry about. And also another thing is that we should also care about an education, because I think tools like machine learning and maybe similar to fast Fourier transforms, maybe similar to all these other things that have been developing. There is a time that they're popular and powerful, and there are times that these things, they go away. So the thing that is important is the story of education, which is another statement by Boris Skinner, which says education is what survives when what has been learned has been forgotten. I find this statement very insightful. In the sense also for the way our learning machines learn to generalize, but also about us being educated in certain methods and then learn them to apply them work. I think things that you finally use and the way you're thinking is far more important than learning one particular technique in machine learning. And I think we have a responsibility to the younger generations to pursue such an education. Thank you very much. Apologies for learning for running so long and maybe missing some.
Thank you, Professor.
Thank you very much for this really brilliant and inspiring discussion and talk. I would like to hear some questions and comments from the audience. I was really impressed by the slide you showed us that a computation that took 1 year in 1997 was performed in 3 minutes today. And really many really inspiring hints in your very interesting talk. Thank you very much for this very interesting presentation. Are there any questions from the audience? Surely Sauro would have had many questions for you, but he wrote me that he has had to go away, and so he will contact you in private to share some thoughts and some questions.
Actually, Petros, I just managed to come back.
Great, Sauro, great, okay.
Just to pay homage to you. I could just follow your presentation very sparsely, and I'm very impressed with your learning procedures, but I'm not able to make any sensible comments. So I'll get back to you privately, because I think we have really a lot to learn. And I wish to thank you again personally for being with us today.
Thank you. I hope to see you in person soon.
Well, let's hope so. Thank you, Petros. And I'll get in touch with you by May. Thanks.
With pleasure.
And Professor Koumoutsakos, do you expect a sensible outcome from the next generation of exascale supercomputing in these learning procedures, algorithms, maybe in the reinforced learning that is so demanding from a computational point of view?
Yeah, I think they would allow us to push things a little bit more, and I think they will. I hope that they will encourage people to think more along the lines of stochastics. So these reinforcement learning algorithms, as I said, they're very expensive, but now they're becoming viable. As you said, 20 years ago, it was forbidden to think in terms of reinforcement learning and such things. But now, in particular, thanks to these exascale computers, most of these algorithms, they're very well suited to parallel machines. I expect that this convergence between numerical analysis and reinforcement learning and other forms of learning or stochastic optimization will be very exciting. And I think it's also very attractive to get people to think along these lines, because yes, we have come up with certain ideas, but I'm sure there are many more ideas that people can come up with of how to combine these two techniques. I think if you start to dig deeper into the reinforcement learning, you will find ideas how to use things that you have experienced already. So the things you have experienced, you put them into memory, and then the way you are accessing memory and you're bringing the events experienced to the problem that you're solving at hand. This is called experience replaying for reinforcement learning. But if you look at it from the point of view of physics, it's very much related to things like importance sampling. It took me some time to understand this fancy name, experience replay, is nothing more than importance sampling. And actually, if you then bring ideas from importance sampling into experience replay and reinforcement learning, you actually, the algorithms that we have are clever physics algorithms applied in computer science. I think this convergence of fast computers, openness and algorithms that we now start to deal with that were usually only for computer scientists, and openness of computer science to physics and vice versa, very exciting times. It's really exciting, and I think it's fantastic for new generations of people. They have all to explore. So I think it's and I think yes, all these exascale machines bring new possibilities that we didn't have before, and I'm looking forward to see what people come up with.
Okay, thank you really very much. Are there any comments, thoughts, or questions from the audience?
Giacomo, if I may, since I managed to get back, Petros, just very quickly, you mentioned, and I'm not sure I really fully understood, but learning from the early stage of the dynamical trajectory to anticipate what's going to happen later on. Did I get you right? Because we tried something like that in a completely different context. It had to do with protein motion. So I wonder whether I got the idea correct. Pardon?
Please go again.
I'm saying
I didn't hear you. Yeah.
Can you hear me now?
Yeah.
Okay. So it seems to me that at some point you were presenting an application where you would train your network using early dynamics in order to anticipate actually the late stage dynamics. Did I get you right? Because this would be something very general. We tried something like that in a different problem, which had to do with protein motion, and it was a kind of mixed success. So any hints or any lesson you might have learned?
Yeah.
I would really
like to another place where I have some exciting results. If you allow me for a second, I'll tell you about my latest favorite project, which is called Learned Effective Dynamics. So it'll be a very convoluted answer to your question, Saur, but I'll show you molecules.
Yeah, please.
So maybe you are with a method of Yannis Kevrekidis of having some kind of small scale simulations. And the idea was to take the small scale simulations and then put them up onto the, actually, let me go back. So the idea is that you do, that's what Yannis, the equation free framework of Yannis,
I know that
you have a micro scale, and then you go to a macro scale and then back down. Now, in my opinion, there, and I have talked to Yannis, I hope I have his blessing. There were two things missing from Yannis' result. How to propagate in the macro dynamics, and how do you go from the macro to the micro? So I believe we have made a contribution there through machine learning by using something called autoencoders. The autoencoders is the same thing as what I showed you earlier about the proper orthogonal decomposition becoming a neural net. So you have now the autoencoders, and you go from up data back to themselves, but you have a latent space. So now the idea, basically, of what we do to Yannis' system is go back here, and now for every one of the micro scale simulations, we have an encoder that gives us a latent space. Now, the latent space may not be physical, but we can propagate information using RNN and LSTM. And I think the RNN LSTM is very important because the dynamics in the latent space are not Markovian. You need to have history. And this history comes to you automatic from RNNs. And then the cool thing is that because you have developed decoders there in the training process, when you think that your stuff has gone bad, you can go back to the decoder and get you into the fine scale again. So this is called learned effective dynamics that we are fighting with reviewers to publish. We get some really good results in Kuramoto-Sivacinski, but I promised you molecules, and I'll show you molecules. So this was some kind of alanine dipeptide, I think. And this is prediction done using molecular dynamics. And this is done at a huge fraction of the cost using this dynamics framework. So that's exciting. That's one direction that I am particularly excited, and I'll be happy to
I definitely smell what
possible connections.
Let's talk about that. That looks very general. It's really fascinating.
It is very general, and the devil is in the details. But
of course,
yes,
as usual.
It can be very exciting.
But I'm familiar with Yannis' work, and I see where you're coming from. Of course, one should sit down and work out the detail. Let's talk, Petros. Unfortunately, I mean, coming to the US is still, we are under ban, as you know. So I don't know. I hope next spring to be there. Anyway.
I hope so too. I hope so too. We can organize things.
Thank you so much, Petros. Thanks for being with us.
Okay.
Talk to you later.
Okay. Thank you very much, Professor Koumoutsakos, for being with us today.
Thank you.
And
thank you for having me. And I hope
you're really welcome. We really enjoyed your very brilliant presentation. And I really hope for myself as well, also for the other speakers, to keep in touch with you with these very interesting topics. And giving you all my best regards, I close this first day of DSFD 2021. And I wait for all of you tomorrow. The two sessions will start in the morning, according to the program that is on the website. And please join us tomorrow morning. Thank you again, Professor Koumoutsakos, and thank all the speakers, attendees, and organizers for this very interesting first day of DSFD 2021. Thank you very much.
Okay. Thank you very much.
Bye-bye.
Have a great day. Bye-bye. Bye-bye.
Bye-bye. Thank you again, Professor Koumoutsakos.
Bye-bye.
Talk to you soon.
Bye.
Bye-bye.
Thank you.
Bye.